So Dr. Balaji Garu is a senior scientist at Center for Fuel Cell Technology, International Advanced Research Center for Powder Metallurgy and New Materials, ARCI, Chennai, where he has been contributing significantly since 2010. He holds a PhD in chemistry from CSR Sikri Karaikudi, along with postgraduate and undergraduate degrees in chemistry from Alagappa University and Madurai Kamaraj University, respectively. With over 2 decades of research experience in hydrogen energy technologies and electrochemical sciences, Dr. Balaji has worked extensively on fuel cells, electrocatalysts, water electrolysis, corrosion, electroplating, and wastewater treatment. His career includes roles as postdoctoral fellow at Itami Institute of Technology, Japan, scientist at SPIC Science Foundation and research associate at SICVI. Dr. Balaji Garu has led and contributed to several national R&D projects funded by DST, MNRE, DRDO, and ARCI, focusing on PM fuel cells, electrochemical hydrogen generation, methanol reformers, flow fuel plate development, and advanced battery systems. He has played a key role in multiple technology transfers, including electrochemical hydrogen compressors, alkaline electrolyzer electrodes, and specialized electroplating process. He has authored numerous international journal publications, patents, and book chapters, and has delivered invited talks in India and abroad on hydrogen energy, fuel cell systems, and electrochemical technologies. His contributions have been recognized with the Outstanding Scientist Award in the year 2016 and included in Marquis Who is Who in the World in the year 2015. Dr. Balaji Garu is actively involved in professional societies such as the Hydrogen Association of India and SAIST, and serves as a reviewer for leading international journals. He has also supervised several postgraduate and doctoral theses, reflecting his strong engagement with academic and scientific mentorship. So I request all the participants to join me together in welcoming our esteemed resource person of session 3, Dr. R. Balaji Garu. Now, without any further delay, I would like to hand over the session to Dr. R. Balaji Garu. Sir, the session is yours now.
Yeah. So, am I audible?
Yes, sir. You are clearly audible.
Yeah. So, thank you for extending the invitation to be a part of this online FDP program. So, thanks for that, and thanks for the introductions, and good evening to one and all. So, basically, the session which I am going to deal is today is about the hydrogen actually. So mostly I would like to touch upon the core aspects of the hydrogen. So that is generation, then storage, because the applied aspects, I think many of them may cover actually. So I would like to touch upon the more core aspects of the various wings of hydrogen energy technology, especially the generation aspects, and then in terms of technological availability for that, and then the storage actually. So these two parts I would like to touch upon the various aspects of that particular aspects of hydrogen generation and then storage. Maybe after a couple of days back, after a couple of days, I may handle another sessions in the Friday, I think so. So in that, I may try to focus most on the fuel cell and its application, especially for transport and stationary applications actually. So with this base introductions about the topic which I'm going to discuss, just I will share the screen just to please ensure that whether it has been displayed there.
Yes, sir. It is getting shared.
Is it? I have put it in slide load mode. Is it visible now?
Yes, sir. Visible.
Yeah. So thank you. So the topic for the discussion is right. Right. We consider as a hydrogen actually. So that is we sometime back we try to understand about the hydrogen is a kind of hazardous chemical actually. So now the scenario has been changed into considering as it's a very good energy carrier, and a lot of scope, hope for especially for the hydrogen, not only in India, all over the world actually. So how this translation has happened actually over a period of time. So that is the journey of hydrogen, that is start from hazard to hope. So that is considered as a very good sustainable energy vector right now. So before getting into the research topic, actually, so the ARCI would like to have a uh, brief about our institutions. It's basically a ARCI is autonomous R&D institution, comes under Department of Science and Technology. So we headquartered at Hyderabad actually. So we have a 9 center of excellence at Hyderabad, and in terms of materials and then metallurgical and well as nanomaterials aspects. And there are two centers. It is from Center for Fuel Cell Technology where I'm coming, and then Center for Automotive Energy Materials. These two centers are functioning at IIT Research Park in Chennai actually. So we have a 25 years of experience in this metallurgical and material research institution and energy related aspect also. And we have a scientific scientist and we do offer research scholar actually. So, and the uniqueness of the research scholar is here that they can register the PhD as a kind of external candidates with any of the NITs and IITs in India, and we will support them for as a kind of full stipend with 5 years, and at the end of the 5 years they will have a research as well as translational research experience with the and ultimately they will get the degree from the reputed institution. So that kind of manpower generation is also one of the key area where we are going to concentrate. The main motto of ARC is that it's a translational research actually. So the whatever the research R&D effort which we are putting has to be scaled up, and it should be scaled up to the demo pilot scale level actually, so that the technology adoption by the industry and the technology viability can be validated within the lab actually. So that is the uniqueness of ARCA, which is compared with other R&D and national institution actually. So we do work on high TRL, that means technology readiness level in all aspects of the technology actually. So that is main motto of ARCA, that is called transnational research. And coming to our center, actually we established in 2004. Actually, we have a 2 decade experience on this hydrogen energy technology, and we occupied about 20,000 square feet in our IIT Research Park. This is a multi-store building. Actually, we occupied about 20,000 square feet, and we have a very good employees in all categories, ranging from senior scientists and technical staff, and then students and other supporting staff. And as I said, the main mandate of ARCA, especially CFCT, is also to kind of technological development in terms of hydrogen fuel cell, and it needs to be validated in a commercial scale so that the technology adoption by the industry is easy. And apart from the technology development, as I said, the knowledge dissemination in terms of manpower generation is also one of the wing of ARCA. So the main motto of CFCT, that is for Center for Fuel Cell Technologies, developed hydrogen-based PM fuel cell technology and its allied area. The major activities of ARCA CFCT is that hydrogen fuel cell, that is low temperature PM fuel cell, and then the hydrogen generation, because the fuel cell comes under the third wing of the hydrogen energy. There are two important steps which are coming from generation and then storage actually. So we do concentrating more on fuel cell along with hydrogen generation. So these are the major two vertical where we are concentrating. And then hydrogen storage in terms of material development, we do work on that area. And as kind of spin-off technology, we do also concentrating on other energy storage devices like supercapacitors and batteries. That is kind of spin-off of, because most of the component which we are using for PM fuel cell and then hydrogen generation can be used for this other energy storage devices like supercapacitors, battery. That's kind of spin-off, not as a main core technology development. So coming to the concept of net zero. So right now we talked about the net zero emission actually. So if you see this periodic table, so that represents many of the elements actually. So right now we deal with mostly on this carbon based actually. So now we try to move towards zero. So if you go back from the carbon, so lithium, so that is a kind of transition where we are talking about more of electric mobility, so that based on lithium ion battery based mobility as well as energy storage aspects. But if you want to achieve nearly to zero, actually we need to go to hydrogen because it's next to zero actually. So if you want to go to zero, the hydrogen will be the pathway, sustainable solution to attain net zero target of international actually. So, but if you see this, as I said, we talked about hydrogen as a kind of hazard actually sometimes back. But yes, it is hazardous actually. Still, the nature of hydrogen is remains same because that won't change depending on the policy of the individuals actually. So it's despite the clear environmental benefits which we have in terms of hydrogen, but it has a though it has a numerous benefit in terms of environmental aspect, but it is highly risk in terms of safety aspect. But there are significant challenges in terms of safety actually, because the wide range of flammability in the air actually, especially in the hydrogen, ranging from 4 to 75, the window is huge when compared with the other gases actually. So in this flammable window, the presence of ignition sources, any ignition sources are there, so these mixers have potential to cause fire or explosion actually. So because of that only properties, we are away from the hydrogen actually. But there are safety standards which we need to establish actually. The radar, it is well established right now. So if you see the history of the hydrogen related accidents and incidents in the world actually till 2023, it's about 755 incidents actually. So if you see that most of them are based on manual error actually. So if you see this 46% is close, about 50% is close to management and organizational errors. Because of that, the incidents happen. And the individual errors are slightly lesser than the organizational point of view. It's only 30. And then especially the job aspects, actually it's about 25. So these are the various percentage analysis of hydrogen related incidents and accidents happened till 2023. And the error, the different error causing for this hydrogen incident accident, if you see the right side of the figure, there are system error and the kind of installation and the material manufacturing error, and then there are 15 above is unknown actually. It's unknown error actually. So if you see this accidental history and then property of this hydrogen, we can clearly understand that the establishment of safe system work actually is essential if you want to handle hydrogen as a energy carrier instead of hazard actually. So that mindset has been changed internationally, and now the people are well aware of most of the working people. They are well aware of handling hydrogen, and it is much safer than the LPG because we handle LPG, but because it's a lighter gas, even if it is escapes, actually it's go very upward direction very easily. So in that sense, actually it's a slightly safer. And then there are various safety procedures are well established and safety equipments are there. So that is the reason that it is driving us to consider hydrogen as an energy carrier instead of hazard actually. So, but if you see that the transition of hydrogen energy will not happen overnight actually. So, because if you see the transition, energy transition from the fuel wood to hydrogen, there is a intermediate pathway: coal, oil, and natural gas. Now we are dealing with natural gas in many automobile sector actually. So instead of that, actually, so if you the hydrogen will be the ultimate energy transition and energy sources and sorry, energy carrier is being considered, but the transition won't happen overnight. So it can be categorized in three different manner. One is present scenario and the intermediate and then ultimate actually. If it is a present scenario, so it's mostly fossil fuel based energy transition, that but all this energy transition will happen through the chemistry actually. So the fossil fuel is being considered as a present scene of energy demand actually to meet out the energy demand. But intermediate is being considered as electric and hybrid vehicles, that is biofuel and synthetic fuel based vehicles and power generation. So these are all being considered as a intermediate state. But the ultimate objective of going with the cleaner and greener energy transition, that can be happen through hydrogen actually. because it's environmentally friendly, and it is carbon-free hydrogen-based vehicles and power generation, because it can be generated away from the carbon route, and it can be utilized away from the carbon route actually. So that's why it's being considered as a green and cleaner fuel for the future energy demand actually. So in that case, actually, when you have a variable multiple energy storage device, because the battery and hydrogen both are being considered as a energy storage medium. So in that aspect, when you have a battery-based energy storage mechanism, why do you want to go with the hydrogen? So if you take the characteristics of every energy storage medium, that is energy storage duration and energy density, power density, and the cyclic life and the self-discharge rate, and in terms of life durability. So in all those things actually, the hydrogen based, it's almost it is also on par with the battery based, but one aspect is that the the amount of energy which we can't store in the level, in the scale level, if you see this, the supercapacitors, it meet out the sudden energy demand, not for sustainable energy demand actually. In the case of batteries actually, yeah, it can meet both sudden as well as long-term energy need, but it cannot be considered as a higher level, especially in gigawatt and terawatt level, because it's a bit difficult in terms of battery-based energy storage device. So in the case of gaseous based, that is hydrogen, so it can be scalable from few watts to terawatts or gigawatt level. So that is one of the major drive of considering hydrogen as a very good energy storage medium like battery. But in these aspects, if you see the cycle life efficiency, because if you have a 1 kilowatt battery and do charging and discharging, say, and you can store 1 kilowatt power, and then you can get back 800 to 700 watts of power from that actually. So the obviously cycle life efficiency is being considered 70 to 80%. Whereas in the case of hydrogen, actually, that is very low, it's 35 to 40, because when you take hydrogen is not existing as such, so you have to generate from some other sources like water or hydrocarbon. So if you again end up with hydrocarbon-based energy storage, then again you will not get the carbon credit. So you have to only depends on the water as a primary source for hydrogen generation. So in this, you have to generate hydrogen from the water by giving electricity and then store it. And whenever you require the power, again you use it in fuel cell, you can get back the power and water. So it's being considered as a battery charging and discharging mechanism. So hydrogen generation and then utilization in fuel cell will be a charging and discharging, similar to charging and discharging mechanism of battery. So in that aspect, it is about, because the reactions, the chemical reaction, if you see this, water plus power will give hydrogen and oxygen, and the same chemical reaction, if you reverse it, hydrogen and oxygen will give power and water. So though the chemical reactions are same, but the efficiency is not same actually. So the amount of input energy is slightly higher than the amount of output energy which we are getting from the fuel. So that is a reason for low cycle efficiency, but there are a lot of scopes for the improvement to increase the cycle life that we will address at the end of my presentation actually. So when come to the challenges in terms of hydrogen energy, so there are multiple challenges. It's not only a one aspect actually. So first you have to generate the hydrogen in a very energy less process actually, that is production, and then storage actually. How we are storing after generation, so how we are going to store the hydrogen, that is also equally challenges, because it's a lighter gas, it occupy more volume. So how you effectively store in a vehicle if you want to carry a onboard hydrogen gas like a CNG? So how you want to store hydrogen, that is a typical challenging steps actually. And then the delivery actually, because we need to transport hydrogen from one sector to another sector, from one place to another place, how we are going to handle the hydrogen effectively. So that is a delivery. And then finally, in what system which we can be used to convert hydrogen into power, whether it's IC engine or it is some other conversion engine like a electrochemical engine like a fuel cell actually. So in each, and apart from this generation, storage, delivery, and then utilization, the safety is also equally important. And establishing the codes and standard to handle the hydrogen is also equally important. So these are all is a kind of system integrations in all aspects of the hydrogen vector. And then coming to the first aspect of generations actually, because this is the various method of hydrogen productions. So depending upon the type of feedstock, because hydrogen is not existing as such, you have to generate from the hydrocarbon or from water actually. So if you generate from hydrocarbon, so again you will end up with a again you will end up with carbon emission like carbon dioxide or carbon monoxide emission. So that is called as a gray hydrogen. If you see the right part of the slides actually, so gray hydrogen which generate from the hydrocarbon along with carbon monoxide and carbon dioxide emissions. So if we have a mechanism to store them, to convert the CO2, because you are generating hydrogen, but ultimately you are parallelly generating carbon monoxide and carbon dioxide. But if we have a storage mechanism to store the carbon dioxide effectively and then convert it to useful product, then that hydrogen is being considered as a blue hydrogen actually. But in both the cases, the feedstocks are same, maybe hydrocarbon. But if you want to completely away from, if you want to be completely away from the hydrocarbon source, the ultimate source is the water actually. So if you do the power from the, if you get the power from the renewable electricity and split the water molecule, get the hydrogen and oxygen. There is no carbon emission in this route. And whenever you require the power, you use it in fuel cell, get the power and water. So that's why it is considered as a green hydrogen. That's what the National Hydrogen Mission is insisting, to generate hydrogen from the water actually. If we see these various methods of generation, because the fossil fuel base, that is natural gas, that is can be steam reformation and the gasification, is a widely adopted internationally. About 95% of the hydrogen is being produced from the steam reformation and gasification method. And if you equip it with the carbon capture and storage mechanism, then it will become a blue. And if you take the next vertical, that is nuclear energy plus water, because get the power from the nuclear energy and split the water molecule. And apart from the power energy from the nucleus, if you can directly split the water molecule into hydrogen and oxygen, and in presence of some catalyst, that is the high temperature electrolysis also can be carried out, so you can get the hydrogen. But these are high temperature operation. It requires some special materials to handle this kind of high temperature electrolysis. But the near ambient conditions electrolysis is feasible, so that can be used from the renewable energy power. So whether it is solar or wind or biomass, and then do the electrolysis or gasification, so you can get the hydrogen with a less carbon footprint. So that is called green hydrogen actually. So depending upon the feedstock and the amount of carbon dioxide emission while producing hydrogen, it is being widely categorized as brown, gray, blue, and green. So the brown is not the coal gasification, because you do the gasification of coal along with the steam, then you will get a CO2 and hydrogen. But the emission of CO2 in this case is slightly higher, about 18 to 20 kg per kg of hydrogen. Whereas in the case of natural gas, because it's a methane actually, it's a one carbon hydrocarbon, so the amount of carbon dioxide emission is slightly lower than the coal based things. So it is about 10 to 12, that is gray. And if you equip it with the carbon capture and storage mechanism, then it has become blue with a low carbon emission per kg of hydrogen. And if you do the electrolysis with renewable energy power, then there is no carbon footprint, it is zero carbon footprint, and that's why it is called considered as a green hydrogen actually. So if you take the renewable energy, because you take the renewable energy, whether it is thermal renewable energy or it's electrical. So if you take directly heat from the renewable energy and do the electrolysis, thermolysis, because the water can be split directly into hydrogen and oxygen at high temperature of 2000 degrees Celsius. Because when you do the without any catalyst and without any materials, you can decompose water directly through thermolysis at a higher temperature of 2000 degrees Celsius. You can get hydrogen and oxygen. But during that separation of hydrogen and oxygen, there may be a possibility for a recombination at high temperature. Again, it will become a explosive things actually. So because of that, these thermolysis routes are still in the R&D level. And if you see this getting the renewable energy from the electricity from the renewable energy and do the water electrolysis, get the hydrogen. So that technology has been widely demonstrated worldwide. So the technology is matured. And the third case, so biomass is also being considered as renewable energy, and do the gasification and get the conversion, and you can get the hydrogen. That is also a green route. And if you see this photolysis, it's nothing but directly getting the power, light energy from the sun and split the water molecule using some electrocatalyst or photocatalyst material, and you can get the hydrogen and the oxygen. That is called photolysis. So among these, all the route, thermolysis, electrolysis, and biomass conversions and the photolysis, the electrolysis routes are a bit matured and technology is being demonstrated. So I will come to the electrolysis route part in detail later. Before that, what is the disadvantage of going with the photolysis route? Because the sun has enough energy to split the water molecule into hydrogen and oxygen directly. So, but fortunately, the water is opaque actually, so it does not absorb any energy. So that's why the water remains as such as water actually. Otherwise, it can be converted into hydrogen and oxygen. So because the sun has enough energy to split the water molecule hydrogen and oxygen. Because of this reason, water exists as water. But when you introduce some electrocatalyst, sorry, photocatalyst, because that material will convert photon into electron, and then that electron is being used to generate hydrogen from the water. So that is called photolysis. The photon to electron, electron into hydrogen. So this is a two-step process actually. So that is called photolysis route. But this process, if you want to carry out, so there is a obstacles actually. So the obstacles of direct photoelectrolysis water are the lack of efficient light absorption, because you have to absorb the light energy, then it should be stable in the water environment, and the absorbed energy has to be converted into electron. Then only you can get the hydrogen from out of water. So there are material which has a very, so the main property of the material should be highly electronically conductive, and it should be stable in water. So these are the two properties essential for any photocatalytic material. So yes, there are materials are there to satisfy these two properties. But if you take some material and which we have a very good electronic conductivity, and it will do the job of conversion of photon into electron and electron into hydrogen very nicely. But that material may not be stable in the water. So, and there are material which are highly stable in water, but the conversion of photon into electron and hydrogen with the electrocatalytic activity or electrical conductivity of the material may not be high. So because of these two regions, identifying a proper photocatalytic material which will perform these two jobs, actually it should be stable in the aqueous environment and it should have a very good electronic conductivity. So that is the major challenge in entire photoelectrocatalytic material aspects. So all over the world, the R&D is going on to get the maximum efficiency, because when you want to convert the photon into electron, electron to hydrogen, the overall efficiency is close to be 9 or 10. So if you could be able to identify a material which can do the both the job and getting the 9 to 10% efficiency, then it is a technological breakthrough. So the TA, right, so far the TiO2, that is a titanium dioxide based material, it's fairly good, which will do the dual job of converting photon into electron, electron to hydrogen, and it will be stable. So there are some fine tuning of the electronic properties, and you have to reduce you have to increase the electronic conductivity, and you have to reduce the resistance. So in order to increase the electronic conductivity of the material, there are some dopant material is being added along with titanium dioxide to get the maximum conductivity, and it should be stable. So because of this, these photolysis route are not being taking place in a technological level, and so it's only in the R&D level. So these are the various institutions which is being involved internationally as well as in India. So those who are working on photocatalytic, identifying a proper photoelectrocatalytic material for performing these photolysis reactions. And coming to the thermolysis, as I said, because if you do the thermolysis of water at high temperature of 2500 degrees Celsius, you can directly split the water molecule into hydrogen and oxygen. But in this case, there is a possibility for the recombination of hydrogen and oxygen, which is being produced. Again, it would come back to water, or it leads to explosion. So in order to avoid the operation of high temperature, people are trying to introduce the chemicals, that is hydrogen iodide and sulfuric acid, in this route, so that the transfer of energy from thermal energy into hydrogen take place at lower temperature, so that you can get the hydrogen and oxygen in the respective compartment. So that is called thermolysis. Here, this technology is also not matured because of some recombination, because you cannot, though it is 2000 degrees Celsius required to do the thermolysis. When you try to introduce this hydrogen iodide sulfuric acid, sulfur iodine sulkyl, you can slightly reduce the operating temperature close to 900 to 400 degrees Celsius. But even in that case, there is a possibility for the recombination of hydrogen and oxygen. So because of these challenges, this technology is also not in mature level like photolysis actually. So coming to the final aspects of electrolysis, that is the only method where we can do get the hydrogen with all the safety and maximum energy maximum energy efficiency. So this is called electrolysis. You can directly get the DC power from the renewable energy, putting positive, because it's an electrochemical cell. You need to have a positive or negative electrode, and you need to have a water does not contain electricity, pure water. So you need to add some ions to make a conduction of ions in between the electrodes. So depending upon the type of electrolyte, whether it is acid or alkaline, it is being categorized in three different manner: acid, alkali, and then oxide-based electrolysis process. But in all the cases, if you see the graph, actually, the amount of energy, electrical energy required to get the hydrogen is slightly higher, because because if you see the minimum potential to require to split the water molecule is close to 1.48 or close to 1.5. That is a theoretical voltage. Electrical energy required to split the water molecule into hydrogen. But in the practical case, there won't be any ideal material, so you have to use some material which is performing better. So because of that, the practical voltage may require more than 2 volt actually. So, and if you do the same electrolysis at high temperature, you can slightly reduce the operating potential because you are some of the energy which is required to convert water into hydrogen is being supplied in two different forms. One is thermal and another one is electrical. So if you give both the energy in, so you can reduce the operating potential cell slightly lower with high operating temperature. So, but in all the case, if you see the right side of the slides, actually, the energy efficiency of the electrolysis is being determined by the operating potential. So theoretically, it's about 1.23, but the practical case is about 1.9 volt actually. So if they see that, if the efficiency is close to coming to 65%, but if you consider, because here there are two steps. If you are getting the power from the renewable, you have to adapt the PV. So you have to consider the PV power efficiency also. So if you consider the 12% PV array efficiency, so 12 into the 0.6y, it comes to 7.8. So if you consider from photon to hydrogen, so the photolysis and electrolysis, because photolysis, in photolysis, the photon is converted into electron, then electron is converted to hydrogen, which is happening within the same system. Whereas in the electrolysis process, we are splitting photon into electron through PV. So next, the electron into hydrogen in electrolysis. So you are separating these two steps and make the efficiency slightly higher than the photolysis route, and these electrode materials are stable, so that this electrolysis route is being considered as a viable route for the generation of hydrogen. So as I said, this is electrochemical cell. You need to have ions to conduct the water into hydrogen to oxygen. So there is three type of electrolyzer. There is alkaline and proton exchange membrane. Is nothing but acid based electrolysis. So you can add either alkali or acid with a pure water, so that you can make the water conductive. So in the case of alkaline, you need to add sodium hydroxide or potassium hydroxide. In the case of acid, you have to add sulfuric acid actually. So this PEM electrolysis is nothing but it's a solid sulfuric acid, because this membrane will act as a electrolyte. It's a solid electrolyte. That's why it is called proton exchange membrane based electrolysis cell. And then solid oxide electrolysis, which is nothing but the oxide ion will take care of the ionic conduction in the water. So, but if you want to perform this oxide ion conduction within the cell, you have to operate the system at high temperature. So because of that, the material has to be withstand at high temperature, and sometimes it may not be possible. So because of that, the solid oxide electrolysis, the state of development is only in the research right now. But this alkaline and the PEM are reaching. Alkaline is well established electrolysis route, so that's why it is being adapted in commercial scale. In the case of PEM, it is maturing to commercial scale because of the cost aspect, not of the technology aspect, because the proton exchange membrane. The membrane is one of the cost component in the PEM-based electrolysis cell. So that way the penetration to the market is slightly slower when compared with alkaline-based system. So, but any electrolysis process, when you want to invest on developing this electrolyzer technology, so there are key aspect has to be considered, especially the cost, and then the cost volatility should not be more, and the purity of hydrogen has to be high, and the safety, because you are handling hydrogen, the oxygen, and the reliability. So these are the major factors which need to be considered when investing in electrolyzer development. And if you see the material aspects, actually, we don't have a, lot of choice for selection of material to enhance the hydrogen evolution reaction. So we have about 2 precious metal and 12 non-precious metals in the periodic table to carry out these hydrogen evolution reactions. So if you see these 2 precious, the platinum and palladium will be the better electrocatalyst material for the hydrogen evolution reaction. And this green iron, cobalt, nickel, so molybdenum, these are all non-precious metal. These are all non-precious metal which can be used in alkaline medium, not in acidic medium. So this platinum and palladium can be used only in acidic medium. And this boron, carbon, nitrogen, phosphorus, sulfur is a non-element, non-metals which can also be used along with this transition metal, so that the catalytic activity of this non-precious metal can be improved. So coming because
sorry for the disturbance.
yeah.
I request the participants to mute their mic. Yes, sir. Please, sir. Please continue.
Yeah. If you see this, as I said, though the theoretical voltage is close to 1.4 volt to split the water molecule into hydrogen and oxygen, the theoretically it is, though it is a 1.4, the practical case it will require 2 volt DC voltage is required to split the water molecule into hydrogen and oxygen. So most of the energy in this case is being used only for the oxygen evolution, not for the hydrogen evolution, because the reaction kinetics for the hydrogen evolution will be faster than the oxygen evolution. So most of the energy is being utilized for the oxygen evolution, not for the hydrogen evolution. So if you could be able to develop a very good material which will reduce the resistance which is being offered during this oxygen evolution, so then you can considerably reduce the energy input for the hydrogen generation. So the anode electrocatalyst, that is also equally important. So depending upon the type of electrolyte, whether it is acidic or alkaline, you can choose the materials. And if you see the chart, actually the ruthenium oxide and iridium oxide is the best electrocatalyst material for the oxygen evolution when compared with other mentioned electrocatalysts in this series. But the basic idea is the selection of material is that when you take any metal which is being used as an electrocatalyst for the oxygen evolution, obviously when you treat as a positive electrode, the metal will try to get oxidized into metal oxides. Actually, that is the nature of any metal. So the energy which is you spend is mostly utilized to convert the metal into metal oxide instead of water into oxygen. So you have to be alert in choosing the material which is already oxidized form. Say for example, ruthenium oxide, iridium oxide, already oxide form of the material which you use as a electrocatalyst. Then whatever energy which you are giving for the oxygen evolution is directly used to generate oxygen from the water. So that is the logic behind the selection of the material. But when you go with such kind of metal oxide based electrode material, what will happen? The metal oxide is normally have a poor electronic conductivity when compared with metals actually. So obviously it has some resistance. So the selection of the metal oxide should be highly electronic conductivity in on par with the metal. So in that case, the ruthenium oxide and iridium oxide will meet the electrical requirement, electrical conductivity requirement on par with the metal. So that's why the ruthenium oxide and iridium oxide based metal has been used for the oxygen evolution electrocatalyst for the water electrolysis. So coming to the alkaline aspects, because there are 3 different type of water electrolyzer. One is alkaline, acidic, that is PEM, and then solid oxide. Solid oxide is not So in the case of alkaline, the advantage is that you can use a non-noble metal-based electrocatalyst. You can use nickel or cobalt, iron. So this kind of cheaper material can be used as an electrocatalyst for the alkaline water electrolysis. And because of that, the overall capex of the system will be low. But in case of disadvantage, because this is an electrochemical cell, so how you can make a very efficient electrochemical cell? This you have to reduce the inter-electrode distance, that is positive and negative electrode has to be close as possible, so that the electron pathway distance can be reduced, so the losses can be minimized, so the efficiency can be improved. So that is a regular logic of constructing any electrochemical cell. So in this step also, so you have to, when you try to reduce the inter-electrode distance as close as possible, obviously you have to avoid the short circuiting. So you have to introduce some separator which will do the gas separation, because each electrode will produce the respective gases, hydrogen and oxygen. So you have to separate this hydrogen and oxygen, otherwise again the explosion will happen. So you have to introduce some separator material which will separate the electrodes and then gas. So, and now if you have a very thick separator material, so then obviously that will also introduce some resistance. So you have to choose very thin separator material so that you can minimize the inter-electrode distance, so that you can increase the efficiency of the electrolysis cell. So that is one of the engineering aspects of increasing the efficiency of alkaline water electrolysis. So the main drawback of this alkaline base, though it has advantage of using non-noble metal based electron material, the main disadvantage is that because the hydrogen production, if you have some small system, the hydrogen production depends on the current which you are pumping into the electrochemical cell. So, but in the case of alkaline, you cannot pump more current, because the maximum current which you can pump based on the material which you are chosen is that 400 milliampere per centimeter square. So if you have a 1 centimeter square electrode area, you can go maximum of 400 milliamps per centimeter square, and then corresponding hydrogen can be produced from the electrode. So, but if you want to produce more hydrogen, so you have to increase the number of cells. So you cannot increase the area of the electrode, because the current, you have a current density restriction. You cannot pump more than 400 milliampere per centimeter square. If you give more current, then obviously the electrode will undergo corrosion instead of evaluation of gases actually. So you have to, that is the bottleneck of this alkaline electrolyzer, so that the system size will be higher. So if you want to produce 110 or 100 kg or 500 kg of hydrogen, then you have to increase the number of cells, so that adds overall capex of the system, and it is also larger in system size is also will be high. So that is one of the disadvantage of alkaline based electrolysis there. Though the disadvantage is there, the people are trying to adopting this technology because of the cheaper electrode material which we are using for the stack fabrications. And coming to high temperature, it is solid oxide water electrolysis, because you have to do this electrolysis product at 500 to 800 degrees Celsius. So in that, most of the material has to be stable. So if you want to identify a material which should be stable in water as well as high temperature, so the only choice which you have is only the ceramic based material. So if you go with a ceramic based material, whether it is an electrode or a separator, then obviously the electronic conductivity is one of the key challenges. It has a less electronic conductivity, but it will be stable in high temperature. Because of these two reactions, actually the material is not stable, and over a period of time, so the durability of the solid oxide water electrolysis is still question mark, so that this technology penetration for the commercial market is still in the nascent stage actually. So the ultimate aim, the alkaline, it is well matured, and solid oxide, it is in the yet to reach the commercialization. And another aspect is PEM, because the one of the disadvantage of alkaline electrolyzer is that you cannot operate more current, you cannot operate the cell at high current density, and you cannot operate the cell. Because of that, you cannot produce more hydrogen in a particular area. So if you want to increase the area, then you have to get the more hydrogen. Whereas in the case of PEM, that is called proton exchange membrane based electrolysis. So the key advantage is this: you can pump more current in a particular area. So up to 1 ampere or 1.5 ampere per centimeter square current you can pump at the same voltage of 1.5 or 1.8 volt. So the beauty of this technology is that the membrane, which will do the job of conductivity actually. Because in alkaline, you have to take pure water and you have to add a salt, KOH or potassium hydroxide, sodium hydroxide, so make the water conductive. Whereas in the case of PEM, you don't want to add any salt with that because this polymer membrane, which is placed in the center of the cell, will do the ionic conduction in both in between positive and negative electrodes. This is a typical like a polythene sheet, and will have a proton within the polymer matrix, which will do when you supply a potential, which will take care of the ionic conduction between the two electrodes, and you have to pass only a pure water to the system. And second advantage is that it's a very thin separator as well as the membrane. Because of that, you can coat electrocatalyst, that is positive and negative electrode material, on the membrane itself. So you can considerably reduce the inter-electrode distance, because inter-electrode distance is nothing but the membrane thickness. So if you have a micron level, 150 micron, 175 micron, or 100 micron membrane, so that is the distance between these two electrodes, only the 100 micron. So you can considerably reduce the inter-electrode distance, and you can increase the ionic conduction without adding any salt, and it also separate the gases which are producing at each compartment. So it's a separator as well as the electrolyte. So it has a dual nature, separator as well as electrolyte, and it reduces the inter-electrode distance. Thereby you can pump more current, and because of that, the overall system compactness you can able to achieve. So that is the advantage of going with PEM based electrolysis cell. And obviously you have to circulate water to the cell. So the anode side, you need to have some plate which is having closed channel, which will facilitate the water molecules to the respective compartment. So because of that, this PEM based electrolysis technology is being matured, and people are trying to adopt commercial aspect also. So here is also, as I said, this Nafion, this is commercial name of the membrane that is called proton exchange membrane, which is one of the most cost component, because 1 square meter is close to 50,000 to 70,000. Because of that, the overall system cost goes up actually. Because the beauty is that it will conduct protons in presence of pure water, and it reduces the inter-electrode distance, and it will also separate the gas molecules. So because of that, the property of it should be electrically conductive. It should be electrically non-conductive but highly ionic conductive actually. So it should be zero electronic conductivity and high ionic conductivity. That is one of the main property of this membrane, and it should be have high mechanical strength and thermal the temperature, in terms of temperature, because when you want to circulate the water, you cannot operate the cell beyond 100 degrees Celsius, because beyond 100 degrees water will get evaporated. So it should be operated less than 100 degrees Celsius, and during that temperature of operation, the membrane should be stable. So this is one of the main component of PEM based electrolysis cell. And apart from the membrane and the electrocatalyst, there is a system, because it's if you want to generate hydrogen from water, you not only require electrochemical cell, you also require other balance of plant actually, because you have to circulate the water to the cell at the anode compartment. When it come out from the cell, it come along with oxygen. So you have to separate the hydrogen. So you have to separate the oxygen and the water, and again you circulate the water into the cell. So you need to have a gas water separator at both sides. In terms of cathode side also, you will get a hydrogen, pure hydrogen, and it may carry some moisture, water vapor. So you have to separate hydrogen from the water separator, water vapor, and then it has to be subject to dryer because it carries a moisture. So you have to remove the moisture and get the pure hydrogen. So the pump and electrical supply system and gas water separator system, these are all ancillary components which is required for the designing of PEM based water electrolysis system. So if you see this national status before the, because nowadays many startups and many companies are coming up for the development of electrochemical hydrogen generator based on water electrolysis. But before that, there are few institutions and have worked on this system level development of water electrolysis actually. So even JNTU has done some small scale system, and ARCI is also taking part in developing a technology based on electrolysis route, and then CSIR SICRI is also involved very early in 80s, and they are in the active for developing such kind of technology. But in all these cases, these are the prototypes developed at various level. And then coming to the alkaline water electrolyzer, because like the advantage of going with the PEM is that you can reduce the interlateral distance and you can handle with the pure water. The same method in the case of alkaline also you can be carried out. So this membrane will be capable of conducting OH minus ion instead of H plus ion. So that is called anion exchange membrane. That is called AEM water electrolyzer. This is a new technology which will also function similar to the PEM technology. But here the advantage is, again, you don't want to use alkali water. You can use only pure water, and then you can favor the gas evolution, hydrogen oxygen gas evolution in 2 different compartments. And this AEM membrane will also have a dual role of separating gases as well as allowing exchanging of ions. So membrane as well as separator. This is upcoming technology, because this technology, the stability is low, because so far it is about 1000 hours of operation has been proven in the laboratory scale. So that's why this technology is not being matured, and that's why the traditional alkaline water electrolyzer is being matured and commercially is being adopted. So AEM is upcoming technology, and because if you want to invest on electrolyzer, the maximum operating hours, it should be a maximum of 30,000 hours of operation. So the cell should be stable up to 30,000 hours. So then only it can be adaptable for the commercial market. But in this, AEM based technology is not matured in terms of durability. So that is only in the R&D level. So if you see this global scenario, apart from the national scenario, so in the whole world actually there are only 33 companies, manufacturers are there to make electrolyzers actually, whether it is alkaline or PEM or SOEC or AEM. So this is the 4 kind of water electrolysis technology. So if you see this alkaline water electrolysis, there are many manufacturers when compared with PEM and SOEC, but in the whole world about only 33 companies are manufacturing electrolyzers. And if you see the performance in all the cases, in terms of energy consumption per meter cube of hydrogen, it's close to 5 to 6 kilowatt hour or 5 to 7 kilowatt hour per kg. So that means kilowatt hour per kg, kilowatt hour per meter cube. So if you want to produce 1 kg of hydrogen from the water, the practical energy consumption in terms of electrical energy consumption is close to 50 to 55 kilowatt hour per kg. So that is the practical, though the theoretically it is required 33 to 35 kilowatt hour per kg, but practical case it can be obtained only at the rate of 50 to 55 unit of electricity per kg of hydrogen. So that's what this entire table is showing, actually, irrespective of the OEM and irrespective of the technology. And as I said, the cost actually, apart from the energy, it's only operating expenditure. The water is water and the electricity. These are the 2 parameters to calculate the operating expenditure of for hydrogen. Whereas in the case of capital expenditure, so you have to consider as a whole system actually, not only electrolyzer. So in this case, the cost of the electrolyzer mostly depends on the electrolyzer as the power supply, because it requires high low ripple DC power actually. So you have to convert the grid power into stable DC power. So 50% of the cost goes to the power supplies and 50% goes to the stack. That is means a hydrogen generator, which will do the electrolysis job actually. So that's why when you want to in this case, alkaline it's about 57 and PEM is about 53. So the most of the cost component involved is 2 aspects. One is power supply and another one is the stack. So that's what this diagram shows. And then coming to the present scenario, Indian scenario of National Green Hydrogen Mission, because you may aware of that, many ministries and our government is pushing to towards the generation of green hydrogen, because the hydrogen is not new. It is being already used as a chemical in various industries. but that the hydrogens are coming from the natural gas actually, not from the water. So that obviously we can end up with carbon dioxide emission. So the main aim of this national green hydrogen mission is that that is steel, petroleum oil refineries, and then fertilizer. So these are the three important sectors. Is already hydrogen is being used for various purpose actually. In the steel, it is being okay. So in this case, actually, people are trying to whatever hydrogen which is being used in this industry is a gray hydrogen. So now the government is pushing to introduce green hydrogen in this sector so that technology adaptability will be easier in the future. So that is one of the major drive for this establishing national green hydrogen mission. So they are targeting these three different sectors: refineries, fertilizer, and then steel making actually. So later part it may comes to the transportation application also. So because of that national green hydrogen mission initiatives, there are various multiple projects or pilot projects are going on in this country in these three different sectors like steel, refineries, and then fertilizer actually. So when you try to use this green hydrogen, obviously the cost, because it's an energy intensive process. As I said, if you want to produce 1 kg of hydrogen, you have to spend 50 unit of or 55 unit of electricity. So if you have a 5 rupees or 8, 10 rupees, depending on the area, so electricity cost. So per kg, if you want to say, for example, 50 unit of electricity, if you want to spend to produce 1 kg of hydrogen, obviously if you have a 7 rupees per unit, so 50 into 7 about 350 rupees or 400 rupees actually. So that is the cost of the hydrogen actually. So if you try to reduce, it is only operating expenditure. So you have to add a capex, and the overall hydrogen cost is close to $6 to $7 per kg. So which is not right now affordable, because if you try to get the hydrogen from the natural gas, the cost is right now is $2 to $2.5, which is cheaper, because you will end up with CO2. Because of that, this cost has come down. But internationally, 95% of the hydrogen is being produced from the natural gas. But in a country like India, we don't have a natural gas resource plenty, so that now our government is we have a enough sun throughout the year, and we have a water actually. And considering these two sources, if you can able to develop a electrolyzer, electrochemical route to generate hydrogen, then we don't want to depend mostly on the imported items actually. So that is the one of the major drive of this green hydrogen mission. So do electrolysis process, get the hydrogen and oxygen, and use it in three different sectors like steel, refineries, and then fertilizer. So these three sectors already they are using gray hydrogen. So they will try to replace this gray hydrogen with the green hydrogen, so that the technology adoption, the handling of green hydrogen technology will be easy. So when you consider that aspects, there are four different aspects: efficiency and durability. There are a system which can have high durability, but the cost will go up actually with high efficiency. So it is a kind of trade-off between selection of efficiency, durability, depending on the capex and apex actually. So that is the cycle when you want to try to invest for the electrolysis technology. So apart from this pure water electrolysis, already you might have seen various hydrogen gas cylinders in the market, which are all produced apart from the because always when you get the hydrogen from the electrolysis route, is always high pure actually. So when you want to use it in fuel cell, we require high pure hydrogen. So if you want to have a high pure hydrogen with low cost actually, the electrolysis will be the better route. But in the electrolysis right now, the energy intensive process, because of that the cost of the hydrogen is slightly high. But right now the same electrolysis process is being employed in chloralkali industries actually, because it's nothing but brain water electrolysis. You do the same electrolysis with NaCl in the water, and you will get the three useful byproduct. One is hydrogen at the cathode compartment, and chlorine at the anode compartment, and sodium hydroxide in the main product actually. So in this case, all the three products are saleable: sodium hydroxide, chlorine, and hydrogen. So in that case, it is also one of the way to reduce the hydrogen cost, because when you do the electrolysis of water, you will get hydrogen and oxygen. The oxygen is not, most of them will not sell actually. So only the hydrogen is being sold, but the energy which is involved for making hydrogen altogether. So in that case, you will get a main product of sodium hydroxide, which is one of the need of any industries actually. So, but you will get the hydrogen as a byproduct actually. So right now, most of the hydrogen cylinders which are available in the commercial is a byproduct of chlor-alkali industries. There are because this technology is similar to pure water electrolysis. Only the material which is being adapted for the electrode is different, and then separator is also different. But if you increase the sodium hydroxide is already being used, and hydrogen is also being sold as a byproduct. But if you use chlorine also, okay, so the chlorine right now is being considered as a carcinogenic material actually, but not like that. So the per capita chlorine consumption when compared with the developed country, India is very low, but you can make use of this chlorine also. So one of the byproduct which is being produced in this technology, and make a viable product like PVC and other chlorine derivatives, then the chlorine is also saleable. So when you sell all the three products, obviously the cost of the hydrogen will also come down. So that is one of the method of reducing hydrogen cost. So coming to our ARCI activities, what we are doing in terms of electrolysis of hydrogen generations. So we mainly concentrating on electrolysis route. Actually, the chemical metal hydrate and photoelectrochemical rate we are concentrating in a low at low TR level, and electrolysis is a main target for us. But the beauty of our technology is that, as I said, if you want to achieve no carbon route, right now we are dealing with more carbon. So there is an intermediate stage of less carbon than no carbon. So the stepway mechanism, if you try to adapt, obviously the hydrogen adoption will be easy. So that is the logic of selection of this technology. Basically, when you do the electrolysis, the energy is an energy intensive process. You will get hydrogen and oxygen at a cost of 50 unit of electricity to spend 1 kg of hydrogen. But if you use it in fuel cell, say for example, you have generated hydrogen from the water and store it in the cylinder. Whenever you require the power, you use the same hydrogen in the fuel cell, how much amount of energy you can get back? So that is the question. But if you use this 1 kg of hydrogen in the fuel cell, which is one of the best energy conversion device in the world to convert hydrogen into power, even if you use that fuel cell, the maximum power which you can get it from the fuel cell using 1 kg hydrogen is close to 15 to 17 unit of electricity. So the input energy is about 50 unit of electricity. Even if you try to adopt best energy conversion engine of fuel cell, you can hardly get 15 to 17 unit of electricity. So there is a gap. Because of that, the overall efficiency is close to 35 to 40%, because 50 is the input and 15 is the output. Obviously, it's close to 30%. So what we thought is the input energy for the generation of hydrogen has to be on par with the output energy which you are getting from fuel cell. Because being a CFCT Center for Fuel Cell Technology, we try to reduce the electrical energy input to generate hydrogen. So we did, apart from the water, we add water in the methanol, that is called reforming. So normally methanol plus water will give carbon dioxide plus hydrogen, but here it is a single carbon hydrocarbon. The emission of CO2 is relatively less when compared with other fossil fuel based system. So we have taken the methanol plus water at a particular ratio and do the same electrolysis route like water electrolysis, and you can get the hydrogen at less than 0.7 volt instead of 1.5 volt actually. So obviously you can reduce the energy consumption for the hydrogen production 1/3 actually. And advantage is that when you want to employ water electrolysis at 1.5 volt, you have to use some metal based material actually. Whereas because if you cannot use any carbon based material for the stack construction, because the carbon will undergo under that particular potential range. So whereas in the case of methanol water electrolysis, you can reduce the we have reduced the cell voltage of operating cell voltage close to 0.5 to 0.7, and here you can use a carbon based material for the stack construction. So that is one of the advantage of in terms of capex, and in terms of apex, you can reduce the energy input. So that is the uniqueness of the technology. When compared with the thermochemical, because the same reaction can be carried out using thermal energy. But in the case of chemical methanol reformer, you have to, the hydrogen purity is question mark, because you need to separate the hydrogen from the carbon dioxide which is coming along with hydrogen, and then you have to purify it. and you have to use it for any application. And it is also high temperature operation. So we overcome these difficulties by developing this electrochemical methanol reformer process. And we started from a smaller single cell level in way back in 2010-11, and we systematically scaled up this electrolysis process up to 5 kg per day. So this is because the input energy is close to 15 to 17 unit of electricity per kg of hydrogen. The same hydrogen, if you use it in fuel cell, we can get back the same 15 to 70 unit of electricity. So the electrical energy efficiency is to 100% actually, close to 100, so that the hydrogen price can be reduced. So recently this technology has been transferred to the industry for the commercial adoptions actually. So this is the photograph of the developed entire system of developing 5 kg per day of hydrogen in our laboratory, and it holds about 3 Indian patents in various aspects of this technology development. And basically this is the electrolysis process so that you can easily integrate with the renewable energy sources actually. And if you see this electrolysis is being considered as a viable route for the hydrogen generation, and there are multiple challenges in terms of cost reductions and in terms of energy efficiency, but all these two aspects can be addressed through developing a novel material. So the developing a novel material, if you see this, there are a kind of key performance indicators. So if you say I have developed a good electrocatalyst material, I have developed a good membrane material, so it has a parameters. If it is matches with the targeted parameters, then this technology adoption will be easy. If you see these all this in this table, the most of the focused area is kind of membrane and diaphragm based development actually. So if you could be able to develop a novel and high performance, less cost membrane or diaphragm material, which will do the job of both the separators as well as electrolyte, then you can reduce the cost of the system, as well as you can reduce the energy input for the hydrogen generation actually. And as I said, the water electrolysis is a direct route of generating hydrogen. So there are multiple routes to reduce the energy consumption, that is called depolarized assist. As I said, most of the energy is utilized for the oxygen evolution. If you try to compromise the oxygen evolution, you can get the hydrogen at lower energy input. So that is called, when you add along with water, you add some urea or methanol or ethanol. These are low carbon hydrocarbon, and do the electrolysis, you can get the hydrogen at a lower energy consumption. So that's what the main concept of depolarizer assisted water electrolysis. And the second advanced electrolysis technology is that the decoupled water electrolysis, because it's nothing but when you do the electrolysis, the hydrogen and oxygens are simultaneously produced in each compartment. But if you try to introduce some time delay by introducing some other third electrode in between the two electrode, you can delay the hydrogen oxygen evolution actually. So hydrogen oxygen will not evolve simultaneously. It will be evolved in with a particular time delay, so that the safety aspect can be improved. So though this concept is novel, the technology is not being matured because it's only in the R&D level. So the decoupled water electrolysis is an advanced electrolyzer technology to generate hydrogen with an efficient manner. And other aspect that, as I said, most of the cost component is that the membrane. So people are trying to eliminate this membrane so that the cost of the system can be considered. So the logic behind this approach is that, so because you have to circulate the water at each compartment to get the hydrogen and oxygen. So it's basically controlling the flow of water actually. So the rate of, so you are operating the system at a particular current density, the hydrogen bubbles started to evolve. So that depends on the applied current density. So as soon as it get evolved in from the electrode surface, you have to evacuate. Otherwise, it will combine with the oxygen within the cell and it leads to explosion. So in order to avoid that, you have to control the flow of water. It's basically fluid dynamics aspects. So you can increase the flow of rate of flow of water and each compartment, and as soon as it get formed on the electrode surface, you try to evacuate from the electrode surface. So in that, this is also one of the fluid dynamically controlled operations, so that you can avoid the introducing a membrane in between the two electrodes, and we can make the capex much cheaper. So this is also a new concept which is slowly evolving, and a lot of R&D efforts are going on in this direction and developing membraneless water electrolysis for hydrogen generations. And apart from these pure water electrolysis, there are multiple momentum across the seawater electrolysis, because we have plenty of sea, and whether can we use directly the seawater for the electrolysis of hydrogen? Yes, you can use it, but the challenge is that apart from the oxygen evolution, you will also get the chlorine evolution actually. So people are trying to reduce the chlorine evolution and try to enhance the oxygen evolution apart from the hydrogen. And apart from the hydrogen evolution, because seawater contains many ions actually, so over a period of time the scaling of layer on the electrode surface will happen. So that also offers various resistance factors that increase the energy requirement for the hydrogen generation. So these are also a very nascent stage actually, but we try to introduce some new concept of because even though the chlorine is present in the seawater, but it will not enter into the electrode surface. So because we have given some protective layer, polymeric layer over the electrode surface, so it will not allow the chloride ion to enter into the electrode surface. It will allow only pure water to enter into the electrode surface, so that you can end up with pure hydrogen oxygen instead of pure hydrogen oxygen and then chlorine. So that is a low TRL level, and we published this results in various international journals. And ultimately, whether it is seawater or it's a normal water, ultimately the cost is one of the factors which will decide the selection of the hydrogen production method. So right now the natural gas method is slightly lower. It's about $2.5 to $3.2 per kg. But when you try to use the nuclear energy, which is cheaper, and then the electrolysis route will become cheaper, it's about $1.84 per kg. Whereas if you use water electrolysis from the grid, it's slightly higher because of the high electricity consumption. And whatever the technology which we adopted now, because we are giving low energy input, so that the energy intensive process can be minimized. So in that, our technology of electrochemical methanol reformer, the cost can be reduced of the hydrogen close to $3 to $3.6 per kg. But so though there are challenges in terms of energy intensive and then capex, in terms of capex, so there are some key measures which we can try to easily adapted. So if you try to adopt this kind of methodology, then you can easily realize the hydrogen mission in India very fast, because the selection of electrolyzer technology is one of the steps of faster adoption of hydrogen, because we should not think about more on the performance and all those things. So we have to reduce the capex as much as possible, and increase the production capability. So the capex cost selection of material should be based on the capex actually. And so because it's a pure electrochemical technology, because the green hydrogen emissions mostly depends on the electrochemical process. So in a country like India, we don't have a much electrochemical background people, and because so that also requires electrometallurgy, because when you want to develop a electrode coating or other metallurgical aspects, so electrometallurgy industries and electrometallurgists has to be realigned, so that the component level making can be increased actually. And apart from the electrolysis stack, other BOP components, balance of plants, especially the power supply and gas water separate supply, dryer, compressor, so these are all additional equipment required to meet the hydrogen mission actually. So we can also concentrate on developing our own BOP components apart from the electrolyzer stack. And the skill is also one of the need of this hour, because as I said, the chloralkali industries which are they are doing on the electrolysis through brain water mechanism. So if you try to adapt their skill for this national green hydrogen mission, is also will pave way for easy adoption of national green hydrogen mission in our country. And then a decentralized electrolyzer plant, because the transportation of the hydrogen is one of the hurdle. So wherever it is required, you can generate on-site. So the on-site decentralized electrolyzer plant is also recommended for the faster adoption of the green hydrogen mission. So there is a debate is going on where will you go for the water. Right now, the desalination technology of seawater is well matured. So you can adopt that technology for getting the pure water, which is essential for this electrolysis route. And as I said, there are multiple awareness program is being conducted among the academic institutions. So you must be aware of what is hydrogen energy technology, what are the key steps which is involved in realizing the hydrogen energy technology. So the various the FTP, like what you are conducting. So these are always one of the key steps to foster adoption of the green hydrogen mission in our country. And if you want to, so though if you try to adapt and you don't try to implement this national green hydrogen mission, how to be sustained? That is also most important. So we have to make our own indigenous materials for development of this component. So that is one of the main steps which we need to take out. And when you want to develop a technology for our country, so you have to think about the recycling, because once every technology has its end of life actually. So the material has to be reused so that it can make the technology sustainable. So we need to have a recycling materials. It is a good research area where we can concentrate more on developing a recycling of the materials, how we can recycling after the end of this electrolyzer life actually. And as I said, though the water scarcity is there, but one of the long-term adoption is that you generate hydrogen from the water and store it. Again, if you want to get the power, you use it in fuel cell, you can get back the water what you have spent it actually. Say for example, you are generating 1 meter cube of hydrogen from 1 liter of water. So when you use the same 1 meter cube of hydrogen in fuel cell, you can get back 800 to 700 ml of pure water. So the water scarcity logic may not come actually when you try to parallelly implement the fuel cell technology along with hydrogen generation technology. And obviously the infrastructure development is also need of the hour, because when you want to try to implement this hydrogen generation program in the mobility sector, especially the transport applications, you need to have a hydrogen filling station. So that kind of infrastructure development is also required when you want to make this hydrogen technology for sustainable. And as I said, when you compare with the battery and then the hydrogen, both are energy storage medium. So which factors which we need to consider? There is a factor which is called energy stored on invested actually, which is nothing but the ratio between how much amount of energy which you spend to manufacture battery or electrolyzer, and how much amount of energy you are going to get back over lifetime using that device. So that is called energy stored on invest. So that if you see this ESOA for, that is called regenerative hydrogen fuel cell. Get the power from renewable, split the water molecule, store it hydrogen and oxygen, and use it in fuel cell. Again, you will get back power and water. So in this case, the ESOA for the hydrogen fuel cell is slightly higher than the lithium battery, because the amount of energy which you want to make 1 kilowatt lithium battery is higher than the amount of energy which you want to make 1 kilowatt electrolyzer or fuel cell. So in that case, the ESOA will higher for the hydrogen based energy storage medium rather than battery. Whereas in the case of efficiency, because the chemical reaction for the electrolyzer or fuel cells are same, but the energy input and energy outputs are different. So because of the material limitation, there are a lot of efforts are going on to identify a ideal material which will reduce the energy input and output as close as possible. So there is a scope for the improvement to efficiency close to 50%. So in that case, this hydrogen fuel cell based energy storage mechanism will take off than the battery in long run. And there are challenges right now. The cost of hydrogen right now is high, and the infrastructure availability is also less, and the supply chain for the materials is also neck within our country, but a lot of efforts are right now going on. The momentum is high. So hope soon we can meet out these, we can come out from these challenges, and we can see this kind of opportunity instead of challenges. So we can come up with a good our own technology for the green hydrogen. And among the there are many startups are coming up in this area for developing novel materials and novel technology and indigenous technology for this electrolyzers actually. So coming to last aspect of the so far we have discussed about the generation aspect. The storage aspect is basically I will try to precisely focus on the storage because the hydrogen can be stored in 3 different forms. liquid form, gaseous form, and solid form. So the compressed gas, because the hydrogen is a lighter gas actually, whatever the commercial hydrogen cylinder which we are using is a steel-based cylinders. In these cylinders, you cannot accommodate hydrogen more than 150 bar because the hydrogen has a nature of embrittlement actually in the metal matrix. It's a lighter gas, so it will, when you try to compress the gas more than 150 bar in a steel cylinder, it try to penetrate in the metal matrix and create a kind of lusters within the metal matrix and create an explosion actually. So the steel-based cylinder cannot be used to store hydrogen more than 150 bar. So you have, but if you want to use it, this compressed cylinders in the transport application, because 150 bar cylinder, the commercial cylinder will have a 0.5 kg of hydrogen at 150 bar. But if you want to cover mileage of 500 kilometers or 400 kilometers, especially for the transport application, you need to carry 5 to 6 kg of hydrogen in the onboard. But under this 150 bar pressure, you need to carry more than 12 to 13 cylinders in the onboard. So that payload of the vehicle will increase. That will not give you the mileage actually. Whether it is IC engine based in hydrogen based engine or hydrogen fuel cell based any engine. So anything, the hydrogen storage, you cannot carry a steel based cylinder. So obviously you have to compress the hydrogen to elevated pressure of 700 bar or 300 bar. So if you want to compress the gases at the elevated pressure, you cannot use steel. So you have to use a carbon composite material based cylinders, which can handle high pressure of hydrogen, and it will also avoid this hydrogen embrittlement phenomena, and it is also lighter weight. But such kind of technology is not available in this country right now. It is being developed actually. So compressed gaseous storage, especially for the transport application, is one of the key challenges. But coming to the liquid aspect, actually, because the amount of energy which you want to liquefy the hydrogen is more than the amount of energy which you spend to for generation actually. So that is, it's energy intensive process. So you cannot use any liquefied hydrogen for any commercial applications. Especially it's used only for the niche area like space or other application actually. So the other form of storing hydrogen is solid, that is in the form of material. So hydrogen has an affinity towards some metal like nickel, boron. This kind of material will form a very good hydrogen bond with the hydrogen actually. So that kind of material which can accommodate hydrogen up to 2% or 3% actually. But there are material which can absorb hydrogen in a physical form actually, not at the chemical form. In this boron, nickel, which will form a metal hydrate actually. You have to apply some pressure and temperature to absorb the hydrogen on the metal matrix, become metal hydrate. The same pressure and temperature range of has to be given if you want to get back the hydrogen from the metal hydrate. So that is called material based, solid based hydrogen storage method actually. So these are the three different method of hydrogen storage: high pressure and liquefaction, and then metal hydrates actually. And there are some materials, but in all those, though the compression can happen up to 700 bar, it is not an energy intensive process. It's relatively low cost in terms of energy. Low, if you can spend low electrical energy to compress the gases up to 700 bar. But there are material which can absorb hydrogen in physical form actually. The carbon nanotubes, the graphene. So these kind of carbon based material have a high porous actually. So in that porous, if you can accommodate hydrogen gas at a elevated pressure and temperature, it can occupy the voids of the material. And if you give the same temperature and pressure, you can get back the hydrogen whenever it is required. So that's kind of carbon based porous material. It's also upcoming to use as a very good hydrogen storage material. So in all these, the major challenges in terms of storage is that the compressed gas, liquid hydrogen, in all the key issues that the volumetric and gravimetric energy density and kinetics, because that is also most important. How fast it get absorbed, how fast you can dissolve. So the kinetics of kinetic and heat transfer. So it's also crucially important when you want to store hydrogen in the form of material, and then the reversibility. So how long you can do the charging and discharging. So store absorption, desorption. So that depends on the material properties. So these are the various key issues in terms of material aspects of developing hydrogen storage actually. So that's called whether it's a physics option or a chemistry option actually. So if depending upon the operating pressure of the hydrogen cylinder, actually, whether it is type 1, type 2, type 3, type 4. So in all these types of cylinders, only the material type, cylinder material type will be different, and the pressure range will also be different. So especially for the type 4 application, it's made of polymer liner and fully wrapped in carbon fiber composite, which is being widely used to have a 700 bar pressure of storage hydrogen, actually. So in this context, ARCI also have developed some material which is carbon-based material. Basically, if we have some seeds like papaya seeds and tamarind seed, which has a high cellulose contents, so you take that seeds and make the cellulose material and do the carbonization, you will get a very high porous carbon area, and surface area of the carbon is also high and porous. So the main challenge in kind of physics this kind of carbon-based material storages. So you have to accommodate hydrogen maximum of 6%. That is the target of DOE, Department of Energy USA target. If you have a porous material which you can able to accommodate 6 weight percentage of hydrogen in this material, then it is through. So in this context, we could be able to accommodate up to 4.7% in the carbon-based material derived from this kind of seeds, actually. But uniqueness is that you can apply only 40 bar pressure at room temperature, because some of the material required high pressure and high elevated temperature. So that is not in our case. So this material can be handled at 40 bar at 30 degrees Celsius with a hydrogen uptake capacity of 4.73. But there is a way to go to reach 6 weight percent. Right now that is going on, actually. So especially for the transportation, people are looking at how to transport the hydrogen, because it's a gaseous form or liquid form. So which form? So liquefaction of hydrogen is energy intensive process. It is not viable. The gas, if you do the transportation through high pressure, then the safety aspect is very less. So the people are trying to transport the hydrogen in form of liquid, whether it is ammonia or methanol. So get the green hydrogen, get the CO2 from the atmosphere and convert into methanol. And methanol is a liquid solvent you can carry very easily. And whenever you want to generate hydrogen, you can get back the hydrogen from the methanol. So liquid organic hydrogen carrier, it's also one of the way to transport hydrogen apart from the gaseous and form. So as I said, that in terms of durability, so the challenges lies durability, efficiency, refueling times, that is basically the absorption desorption cycles, and then cost. So these are the major aspects of challenge in terms of challenges for hydrogen storage. But apart from this material and then challenges for hydrogen generation storage, the awareness is most important, actually. So when you have when you are aware of the problem which is lying in front of you, then you can obviously end up with a solution. So the awareness is one of the key element. So in that context, 1.008, this is atomic weight of hydrogen. So in internationally, 8th October, which is representing the atomic weight of hydrogen, is being celebrated National Hydrogen Fuel Cell Day. So once you start to celebrate these kind of days, obviously people will more aware of the technology, and they will also come up with a solution for the existing challenges. So in that context, we also celebrating last 8 years National Hydrogen Fuel Cell Day, and by conducting various workshops and conferences and panel discussion and demonstration, so that people can mingle with us to come up with the solutions and innovation to realize this national green hydrogen mission. And with that, I will stop here, and I will take up a few questions if you have, actually. So thank you for your kind attentions.
Thank you very much, sir. Now the session is open for the question and answers.
Thank you, sir.
I request participants to ask the
I think
questions.
there are a couple of questions in the chat box, I think so.
Yes, sir. Yes, sir. Already questions.
So I will take up one by one, actually. So there is a questions from I think. So question from Shaik, actually. So what about the pressure level, which means it's required for practical compressed hydrogen gas storage? Actually, right now the pressure range which is required for the transport application is close to 700 bar, actually. So when you want to have a onboard hydrogen like CNG, but whatever the CNG compression which were commercially is being used to 8 to 9 bar, whereas in the case of hydrogen we need to have a 700 bar cylinders on board, so that you can cover the entire range of 400 to 450 with a fuel cell based electrochemical conversion device actually. So the 700 bar is required for the transport applications, especially for stationary applications. Depends on the application end. It may be a 150 bar or 300 bar actually, but especially for the transport application we require 700 bar pressure. Yeah, obviously we will share the PPT. No issues on that actually. So if any questions, then I can answer that.
Sir, we have one more question from the participant, Dr. Rojo Korean Daniel.
Yeah.
So the question is, does the hydrogen economy really make sense when batteries are generally becoming cheaper each year? So that's the question posed by Dr. Rojo Korean.
So, so I think he's comparing in terms of cost aspect. Am I correct? Hello.
Dr. Rojo Korean, can you please confirm about the question?
Yes, sir. Mainly the cost aspect.
Yeah, I mean, yeah, I agree that because the cost aspect right now, the lithium battery is slightly lower, but the cost is because of the volume actually. It's not because of the technological fact actually. Because right now the volume of hydrogen-based mobility or transport stationary application is less. Because of that, the system cost and all is right now high. But once if you try to adopt this technology, there is a difference between cost and price actually. So the price component is slightly higher because of the low volume actually. But the cost aspect, yes, there is a scope for a reduction of the cost in terms of various technological breakthroughs. And once you try to adopt the new technology, obviously the cost will come down actually.
Thank you, sir.
Yeah.
So Mr. Harshit, Yatam Harshit had raised.
Yes, sir, I have a question.
Yeah,
Sir,
please.
can you hear me?
Yeah, I could hear you.
Good evening, sir. I'm Harshit from Automobile Engineering Department, Godavari Institute of Engineering and Technology. Sir, I wanted to know about your opinion on one thing. Like from your perspective, according to your research, what is the one important improvement in the technology that would make this hydrogenized fuel more practical for everyday use, sir?
No,
Means what is the
basically,
technological break that needs to happen? Like from only your perspective, your opinion on this.
no, can you repeat the question? I mean, there was some disturbance during that.
Can you hear me, sir?
Yeah, right now is clear.
Yes, sir. Means I just wanted to know your opinion. Like you have done a lot of research on this.
Yeah.
Like what is the technological breakthrough that needs to happen? Like there is a one stepping stone, sir, for everything. Like for mobiles, for example, for mobiles or electric vehicles, like high capacity batteries that made everyday usage possible. Like same thing for hydrogen. What is the technological breakthrough that needs to happen?
So the basically the good question actually. The cost of the hydrogen actually. So because you will have a conversion device like fuel cell, it is on board, and you have electrolyzers. That is also there. But only thing is how effectively you can generate hydrogen, because again if you end up with fossil fuel, then obviously the carbon emissions, that is more. So the entire world, India is also committed to net zero by 2070. So in that aspect, the carbon emission has to be minimum. So to achieve the target, definitely we need to compromise on some aspect, especially in that aspect. Right now, the cost of the hydrogen, as I said, it's about if you want to generate from the water, because there is only a source which will not emit any carbon. So if you take that technology for the adoption, right now the cost is depends on the energy input actually. So the energy input is slightly higher right now, but there is a scope for a reduction up to 40 unit of electricity per kg. So the cost of the hydrogen is right now high because of the high electricity cost actually. So the cost of the hydrogen is nothing but cost of the electricity. So if you reduce the electricity cost much cheaper, then obviously the hydrogen cost will come down. Once the fuel cost is very less, then obviously everything will be on road, whether it's a electrolyzer, whether it's a fuel cell. The fuel cost is low, then obviously fuel cell and fuel generation technology will also be low actually. So that's why the government is actively engaging the renewable energy, because more and more renewable energy, if you get it, that the cost of the electricity will come down. Once the electricity cost comes down, this hydrogen cost will also be come down. So the technology penetration rate will be faster actually.
Okay, sir. Thank you, sir.
Okay,
Rangarajan had a nice question. I listened to your talk. It was very nice, interesting presentation.
Thank you.
I would like to know any opportunities for graphite in your what are the real challenges and really people are using
the material.
graphite.
There are a lot of opportunity for the graphite, especially in the terms of fuel cell actually, because any electrolyzer or fuel cell, it is a repetition of cell component actually. So if you want to have a high power capacity fuel cell, or if you want a high capacity electrolyzer, especially the fuel cell, we can use any graphite based material for the separator plate, which will do the hydrogen flow and air flow to the respective electrocatalyst material. So it is called flow field plate actually. There is the graphite which are embedded with the polymer, because graphite has a porous in nature. So it will allow the gas permeation between the surfaces actually. So we have to control that porosity by making the composite carbon and composite graphite, so that it will be impermeable to the gases. Once if you have a very planar graphite, very thin graphite plate, so that can be used as a separator material in fuel cell stack fabrication. So you can make a desired flow channel over the surface of graphite, and you can use as a bipolar plate for the fuel cell, especially for the stationary application. Especially the fuel cell is being considered as one of the backup power for various data centers actually. So the stationary power hydrogen fuel cell, the graphite is a very good bipolar plate or a gas separator plate for making various fuel cell stack actually. There is a scope for graphite based material, especially for the fuel cell applications.
Okay, thank you. I think it means a lot of technological people. We got a lot.
Yeah.
Thank you.
Thank you.
So if further questions are there, so because of as we are nearing to the session 4, so we would like to take up further questions. If there are any, please send us through the group so that we can communicate the same to Dr. Balaji Rangarajan sir.
Yeah.
So that he can answer us. So thank you very much, sir, Dr. Balaji Rangarajan garu. So it is our we are very privileged to have you as a research person. The session is very informative, and you have provided us not only the basics of the hydrogen production routes and then generation, but you have also given us a lot of research insights and the pathways for us, the young researchers, to proceed with. So thank you very much, sir, for the very insightful session, throwing light in the different aspects of hydrogen and hydrogen fuel cell technology.
Thank you.
Sir, our coordinator, Dr. J. Jayanand Kumar, sir. Jayanand, sir.
Srinivas Reddy.
Sir.
Am I audible? Ready?
Yes, sir, you are audible, sir.
Sir, I'm Dr. Jayanand, sir. I'm
nice to meet you, sir.
I really enjoyed a lot, sir, because the way you are presenting the content to the maximum possible extent for the benefit of all the participants. Almost around 130 participants still are there, and it shows how much they are attached to the delivery methods and the content. I really appreciate. I would like to share a few points from my inputs, that you are basically working in this International Advanced Research Center for Metallurgy and New Materials. That's a DST center at Chennai.
Yeah.
Is it, sir? So
yes, sir.
Is it attached to IIT Madras Research Park?
No, we are not attached with IIT Madras actually. It's we are rented at IIT Madras area. That's all.
Okay.
So it's not attached, but we have collaborations, but we are not administratively engaged with the IIT.
Okay.
So
And this particular hydrogen and the difficulties with carrying the hydrogen, for a lot of research scope is there, and it's a green field basically for most of the researchers. So all the researchers and the participants can look into this particular aspect. And you are, you said that National Hydrogen Fuel Day is being celebrated on 8th October. So we would like to take up this, sir. And,
definitely, we will share you the invitation. Every 8th October we are celebrating. We will share you the invitation, and participants can encourage to participate in that.
Okay, sir. Great, sir. Sir, one more thing is that our another resource person yesterday, Professor M.V. Reddy, sir, he joined from Canada, and he is also actively working in this particular area, sir. In what is called different materials that can be used for energy storages. Storage. So he's the person who, interacted with you during your, session, sir. Sir Reddy Garu, are you there, sir? Sir M.V. Reddy, he joined, he interacted with you, sir. So
yes, thank you.
Yeah, Professor Reddy Garu, thank you, sir. Thank you once again for sparing your time and being a participant in this session also. So I really appreciate, sir, your presence in this session. So thank you very much, sir. Thanks for your detailed elaboration and the difficulties and the challenges that are going to be addressed by our young engineers and researchers. We will like to work with you, sir. Thank you very much, sir.
Thank you all.
Thank you, sir.
Srinivas Reddy.
Yes, sir. So thank you very much, sir. So
can we conclude, Srinivas Reddy, this session? Srinivas Reddy.
Sir, am I audible, sir?
Yes, you are quite.
Yes, sir. Sir, we have the resource person of the next session also with us, Dr. Kaushik Rajashekara. So we welcome you, sir. Dr. Rajashekara, sir.
Okay, can you hear me well?
Yes, sir. You are clearly audible, sir.
Okay, I can share my screen.
Oh, great. Sir, I'm very much honored. I will welcome Kaushik ji. Hello, am I audible?
Yeah, I can hear you well.
Great, sir.
Can you hear me?
Yes, sir, very much.
Okay.
Srinivas Reddy, could you please introduce our resource person?
Yes, sir. Sir, so it's my privilege to introduce the resource person for session 4, Dr. Kaushik Rajashekara, who holds an outstanding academic foundation beginning with BS in Science and Mathematics from Bangalore University in the year 1971, followed by BS in 1974, MS in 1977, and PhD in the year 1984, all in electrical engineering from the Indian Institute of Science, Bangalore. And he also holds an MBA from Indiana Wesleyan University, Indianapolis in the year 1992. So building on this strong educational background, Dr. Kaushik Rajashekara has developed an illustrious career of over 5 decades, serving in influential roles such as Hugh and Cranz Cullen Distinguished University Professor at the University of Boston, Distinguished Professor at the University of Texas Dallas, and Chief Technologist at Rolls-Royce Corporation, and Chief Scientist and Technical Fellow at Delphi General Motors. His exceptional professional journey has earned him selection to the U.S. National Academy of Engineering, along with international fellowships in the engineering academies of China, Japan, and India, and fellow status in IEEE, SAE, and the National Academy of Inventors. Dr. Rajashekara's groundbreaking contributions to electric, hybrid, and fuel cell vehicles, electric and hybrid aircraft propulsion, renewable energy systems, power electronics, and microgrids have been recognized through prestigious honors, including the Global Energy Prize in the year 2022 and IEEE Medal for Environmental and Safety Technologies in the year 2021 and the Richard Harold Kaufman Award also. A globally influential researcher, he has over 14,000 citations and an H index of around 60 and more than 300 indexed publications to his credit. So he got a citation about 6,000 since 2020, which is reflecting the enduring impact of his work on clean mobility and sustainable energy technologies. So we are very honored to have you as a resource person with us, sir. So I request all the participants in welcoming Dr. Kaushik Rajashekara to our FDP. Thank you, sir. Now the session is yours.
Thank you very much. Thank you for the introduction, and thank you for including me in this week-long session. So I'm going to talk on the power electronic systems for electric, also electric hybrid. I didn't include the word hybrid there, but some hybrid is also there. So it is mainly power electronic systems for electric and fuel cell vehicles. And so right to start with, I'm going to present what are the challenges of the electric vehicles with respect to the battery or power electronics, electric machines, and then what are the present trends, and then I will talk about the power electronics aspects. So I will cover some aspects related to power electronics and power electronics for EVs and HEVs. I hope you all have some basic course on power electronics. Anyway, I will keep it at a very high level. And the inverters for propulsion, PWM rectifiers, commercial power electronic units, and challenges and targets and wide band gap devices. And then these are some of the items I will address. And so the basic electric vehicle technology is very broad. So it includes propulsion technologies such as power electronics, AC or DC systems, motor technologies, motor selection, many things. I'm not going to go through every aspect here. And then another thing is the battery technology, and then the battery charging. Then how do you put all of them together? The vehicle system integration. Then we need to have a good infrastructure like charging, or if it is a fuel cell vehicle, how to fill up the hydrogen, and what is the effect on the environmental, how we are going to benefit by adding all these hybrid electric and fuel cell vehicles, how to improve the overall environment. So these are all some of the issues that need to be considered in commercializing the electric vehicles. So now let us look at the propulsion system challenges and trends. So as I mentioned earlier, we have electric vehicles, hybrid vehicles, plug-in hybrid vehicles, fuel cell vehicles. So the architecture is not very different from each other. For example, everything has to be driven either by the engine or the electric motor. In pure electric vehicle, the power is supplied by the battery, and then it is supplied to the electric motor. Electric motor drives the wheels. So there is no engine there. Whereas in a hybrid electric vehicle, there is also an engine in addition to the electric motor and the battery. So the engine will help the electric motor as needed or the other way, depending on the architecture of the hybrid electric vehicle. Then plug-in hybrid vehicle is exactly like a hybrid vehicle, but you can plug it in the night time. For example, Toyota Prius, you cannot plug it in. Whereas if it is a Prius, PHEV, or Toyota Prime, that has a there is a plug-in hybrid vehicle, so you can plug it in, so you can drive it as a pure electric vehicle for certain distance. For example, Prius Prime has 28 or 30 miles of pure electric vehicle range. That is about 50 kilometers. So as long as you are driving less than 50 kilometers a day, then you don't need to add gasoline at all to your vehicle. So that is the plug-in hybrid vehicle. Fuel cell vehicle is same as the battery electric vehicle. Instead of a battery, you have a fuel cell supplying the electric power. Of course, there will be some battery, but that will be a smaller battery when compared to the actual battery electric vehicle. So this diagram here, it shows how the different components are connected to each other and what are the different systems or subsystems in an electric vehicle. So you have a motor, and the motor gets the power from the battery, but the battery is DC and the motor is, these days everything is all AC motors. All the electric vehicle manufacturers use the AC motor. So that DC has to be converted to AC. That is done by the inverter, which provides the variable frequency, variable voltage. And there is also a converter which converts the battery voltage to the required voltage at the input to the inverter. For example, at the inverter input, you may need 800 volts, but the battery is 400 volts. So this converts, means it boosts the voltage that is required. But if they are similar voltages, battery and the inverter input required, then you may not need. So this converter is not being used in many of the vehicles. In some vehicles, it is used. And then there is another converter that is a DC-DC converter, which converts high voltage battery to 14 volts, because we need 14 volts for all the accessories, right? Because your lighting needs all the door openers, motors, and everything is 14 volts. We call it hotel loads. All the accessory loads are at 14 volts or 12 volts battery, basically. So that is done by this converter, DC-DC converter. And then there is a charger. So we plug it in and then it charges the battery. So the power electronics is required in all these systems. Okay. So that is the basic architecture of an electric vehicle. So what are the challenges right now? I think I will close this and I put it in mute because, yeah. So I had to close because it was coming on my way. All the pictures were affecting my screen. So, battery. Everywhere, this is the same problem. Even though electric vehicles are more than 100 years old, at that time also there was a battery issue about the range, and today also we have the same issue. But the battery technology has advanced so much when compared to what it was even 20 years ago. Range anxiety is coming down, but still it is not as much as we want. It all depends on how long you drive. For example, in United States, people drive more than 1,000 kilometers a day. So then every time they have to stop for charging for 1 hour, all those things, then it is not good. But there are very fast chargers are being installed. So range anxiety, cost Cost is the battery, because most of the batteries right now present based on the lithium ion batteries. Lithium is quite expensive and it is coming mainly from China. And so the price is high. And over the life, battery degradation, the life of the battery can also go down, then you need to change. And also environmental impact. For example, you have to use the batteries, then you have to whole manufacture the whole system, right? That also affect the environment, and also recycling will affect. Then you have to control the battery temperature. That is important. Battery has to be maintained at a certain temperature. Otherwise, it degrades faster. So, as I mentioned, raw material supply chain issues, these are all some of the issues. Then the charging infrastructure. What are the issues? Charging infrastructure itself is an issue. We don't have enough fast chargers. So we want our electric vehicle to be charged as fast as we can fill up the gasoline into our internal combustion engine vehicle. So that is what we expect, but that is not there still. But companies are working on it, are close to it, close to working on it. Not exactly, it may not meet the same target. Then what is the impact on the battery life? Because we use a lot of fast charging now. Even work is going on to develop 1 megawatt fast chargers. Now it is about 150 to 300 kilowatt fast chargers are becoming very common. So when you charge, means using a fast charger, you are putting a lot of current at in a small amount of time. So what is the effect on the battery? And what will happen to the grid if thousands and millions of vehicles are connected to the grid? So how does the grid is going to stand? Do we have enough capacity? That is another issue that is being addressed. Then installation and maintenance costs for the chargers, and also the standards. For example, there is no still particular standard for the connectors for the chargers. For example, in China, they have a different standard. In Japan, CHAdeMO. In North America, more or less now, companies like GM and Ford are using more and more of a Tesla standard. So there is no particular standard that needs to be done. And also in electric vehicle, right now, there is no particular standard for the voltage. Automotive manufacturers, different automotive manufacturers have different voltages. More or less, many of them use around 360 to 400 volts as nominal voltage. Some are using 800 volts, some are 920 volts. But in few years, more and more companies are tending towards 800 volts as the battery DC link voltage, or the DC link voltage may not be the battery voltage, DC link voltage for the electric vehicle system. And also charging speed versus battery size, and also thermal management. Motor. Right now, we have most of the, or almost all of the EV manufacturers, they are using the permanent magnet motors. And permanent magnets are quite expensive. Again, it is coming from China. So that is, and also China can increase the price at any time they want or decrease it. So that is happening. So we want to have a efficiency at high speed, thermal management, and rare earth material dependence. That is the one it's on lithium ion. Size and weight, because we want it to be smaller. In electric vehicles, everything has to be small and less weight, because then you don't use so much of energy for propel the vehicle. Otherwise, your range will decrease. Okay. Manufacturing cost efficiency, motor control and efficiency optimization. We want to have the efficiency maximum efficiency throughout the speed range. And we want to have a smaller unit, so we want to integrate the power electronics and the electric motor, everything into one unit as much as possible. And then there is a power electronics. Again, there is a challenge related to the efficiency and heat management. And we want to have a highest power density as much as possible. Reliability, for example, we use a silicon carbide devices, IGBTs, etc. What happens if they blow? And also cost, electromagnetic interference, because we want to make sure that they do not interfere, because these inverter, they switch at high frequencies, so they can generate electromagnetic conducted and radiation electromagnetic interference. So that needs to be contained. Operating temperature. We want to operate at as high a temperature as possible so that our cooling requirements will reduce. So that's why now more and more companies are using silicon carbide devices. We'll come into that. And the standards. And also availability of high temperature components. It is not enough if you have a silicon carbide or gallium nitride devices which can operate at high temperature. What about your capacitors and several other passive components? Are they available at the temperature? That is another issue that needs to be considered. So these are some of the challenges still in the electric vehicles. So then, as I mentioned, batteries. So right now, almost all the manufacturers, they use the lithium ion batteries. So that is the one that is used, and lithium ion cobalt battery, lithium ion manganese battery, and lithium ion phosphate battery. Lithium ion phosphate is safer than the other two batteries, even though it is a lower energy density when compared to the other type of batteries like lithium ion or lithium manganese, but it is safer. So they are all switching over to lithium iron phosphate batteries. And all these batteries they use right now graphite anode materials. So the next trend is to go for, so yeah, with lithium ion batteries, with the lithium iron phosphate, these are all some of the vehicles which can still provide for example, the Zeekr from China, it can provide 1,000 kilometers on one charge. And they can charge 10 to 80% in 10.5 minutes. So there are a lot of advancements in China. China is number one in the electric vehicles, much ahead of the United States. Even the General Ford CEO commented on the other day, we have to catch up with China. They are much ahead of us. Even Europe, they call it the China speed. The speed at which they are building and they are doing it is, they cannot catch up with it, with China. So they are much advanced in electric vehicles. Of course, they are also advanced in the hydro and renewable energy and many other technologies gradually taking over from the United States. And this car, for example, this also again based on lithium-ion battery, Maxtro. This is an extended range electric vehicle. Extended range electric vehicle is like a hybrid vehicle. There is an engine, but when the battery charge goes below certain percentage, if the depth of discharge reaches say 20 or 25% or 30%, they can set it up. Then the engine will turn on and charge the batteries. So you can go a long way. That is more than 1,000 kilometers, 1,300 kilometers you can go with this one. So without even filling up the gasoline tank. The next advancement in the batteries is the solid-state batteries. Now a lot of companies are working on the solid-state batteries like QuantumScape and also Factorial and many other companies, Samsung. So the idea is, I'm just giving a brief introduction to what are the advancement in electric vehicles. So solid-state batteries, they are much safer and also they have a much higher energy density, reaching to about 500 watt-hour per kilogram. And so you can have a range of more than 1,000 kilometers with this type of batteries. So for example, Samsung's EV battery, so they already tried these vehicles, but it is likely to go into production in 2027, I think so. Yeah, mass production from 2027. It can provide 900 kilometers range, charged in 9 minutes, 500 kilowatt hour per kg, 20-year warranty, no combustible liquids, and currently being tested. Even Mercedes-Benz is testing these batteries. And Toyota has promised a 900 plus mile range electric vehicle. So that is more than 1,500 kilometers. So if you have that one, I think this type of vehicle, of course, the cost, we have to see if the cost is lower for India. Even with lithium-ion batteries, India is fine because in India, people don't drive as much a long distance when compared to in the United States. So with solid-state batteries, it will be much better, but it will be quite expensive for several years. So, for example, QuantumScape is specializing in solid-state battery technology, and yeah, they are very much ahead in this area. And Samsung is there, and several other companies are working. So there are also other batteries technologies are being investigated, like lithium sulfide, sodium-ion batteries. They are coming up. I think I will tell you in the next slide. Lithium air is the ultimate battery technology. It is almost equivalent to the energy density of gasoline, but it is a long way to go. Sodium-ion technology is the one that is being investigated, particularly in China. They already demonstrated this type of vehicles. And also even in the United States, for grid energy storage, sodium-ion battery technology, they are installing the grid energy storage batteries based on sodium-ion technologies. This is much cheaper, or I won't say cheaper, lot less expensive than the lithium-ion batteries. And also, sodium is abundant. Everywhere you get it. You don't have to depend on China, other countries. So this technology is being explored, and CATL is a well-known battery company. 50% of the batteries in the world are produced by the CATL in China. So they tested it. They have achieved up to 200 watt-hour per kg. And this is the sodium-ion battery-based vehicle. So there is a lot of work going on the sodium-ion batteries. Then once this technology develops, then we may not need the lithium-ion batteries also. So it is because it's a lot less expensive and it is available everywhere. So the next trend in the electric vehicles is the 800-volt systems, as I mentioned earlier, because we are switching over to 800-volt system. The reason is higher the voltage, the current is less, so you don't have to have a thick cables. And and also you can charge faster. So you can put more current for the same power. You can put more current into the battery, so the batteries can be charged faster. So several companies are working on this one. They are already in the market, like Hyundai Ioniq 5, Mercedes-Benz is also selling. So there are several other companies are working. By 2026, the majority of the vehicles may be 800 volts, or by 2030, almost all the vehicles will be based on, all the electric vehicles will be based on 800 volts technology. But there are challenges, because then the insulation has to be higher, because it has to take 800 volts. And also more aspect has to be considered related to the safety in the system. So that comes to the packaging, and they are enclosed, and those things. There are some of the issues that needs to be addressed. Then infrastructure. Charging infrastructure is another thing that has been put a lot of effort on this one. Of course, there are more than 100,000 public charging stations in the United States itself. And Tesla has more than 27,000 individual superchargers in the United States, and globally more than 55,000 of them. So there are a lot of chargers. For example, this is near Costco, and also there is a trend towards integrating the photovoltaics and the grid and everything, and also put a high energy storage system. This is not for not the battery inside the vehicle. Battery is inside this vehicle. This has to be charged, but there is an external energy storage, because when you connect so many electric vehicles to a station, because one station is capable of sometimes even 100 vehicles can be charged, then the grid can suddenly get affected. So grid has to supply the sudden current, that much of current. So the battery is faster than the grid. So the battery, energy storage battery, or BESS, battery energy storage system we call it, and that can supply faster, then the grid can gradually take over. So we can have the different systems are considered. For example, the DC connected system, you have a grid, transformer, DC, and DC link and DC converter. You charge vehicles like this, or you can have a transformer. There is an AC, DC, and AC to DC, DC converters. So, and also you can connect the photovoltaic here, or the DC converters. You can put another DC converter here and connect the photovoltaic system, or it is already shown here, photovoltaic DC converter here or here. So if it is closer to the ocean, this charging stations, then you can also use the offshore wind. Then that can also be integrated into this charging system and connected to the grid. So as long as you charge the electric vehicles using the renewable energy sources, then you don't have to worry about the emissions. But if it is charged using the coal-fired power plants based electricity or natural gas, then instead of emissions, At the urban areas, it will be at somewhere in the rural areas or very far from the cities. So that is still that challenge has to be addressed. So that is why more and more countries are installing the chargers based on the renewable energy sources. Then the another advancement that is going on in the electric vehicle is wireless charging. Many companies are working on the wireless charging system. So you can, this is the one. So drive over this pad up, it automatically charges. You don't have to get down and all those things. Basically, so this is a 3-phase system, AC-DC conversion, and this system is inside your car. There's a transformer. The primary of the transformer in this side, and the secondary of the transformer is on the other side. So you can charge the batteries. So many of the fleet vehicles are being exploring this type of wireless charging. There are, for example, rental vehicles. They don't want to be doing all those things. So when they return the car, they can as well park it there and then they can go and it automatically gets charged. So Oak Ridge Lab has recently demonstrated 270 kilowatt wireless charger, but still it is not as much commercially available like the regular chargers. Then there is another work going on in the V2G system, that is vehicle to grid, grid to vehicle. So this is also to be incorporated in almost all the electric vehicles in the next few years. Means if you have parked your vehicle inside your garage and then there is no power in your house, and then you can use the battery inside the vehicle to power your house. Or if there are a number of vehicles parked there, for example, in the workplace, hundreds of vehicles or thousands of vehicles are parked, they're all sitting there from morning to evening. So they can supply those batteries sitting inside those vehicles can supply the energy into the grid, so that grid can be stabilized, so that we don't have to build more power stations. And also when there is a peak demand, particularly in the afternoon time, these vehicles can supply the energy to the grid so that we can reduce the power that is drawn from the power stations. So this is the vehicle to grid and grid to vehicle. So in addition to you charge the vehicle using the grid, so these are all being charged, and then you can also power this whatever the energy stored here when not being used, when parked, you can the electricity can go into the electrical grid. So that is some of the things. Now, for example, these are 22 kilowatt bidirectional liquid cooled onboard battery charger. So you can have both ways. You can use it for charging the batteries, and also when the vehicle is parked, you can use it for providing the power to the grid. So with that introduction, what are the trends in the electric vehicles, where we are now as far as the technologies are concerned? So how the power electronics is coming into picture. So as I mentioned earlier, now we'll go a little bit more into details of power electronics, because there are 130 people. I'm not sure how many of them are power electronics or electrical engineers or mechanical engineers. I'm not sure. I will try to keep it at the high level still. So we have the electric motor. There is the propulsion motor. And then we need the inverter, as I mentioned. And there is an onboard charger. They all use the silicon. Right now, they are all using the silicon IGBTs, and most of them are already converted to silicon carbide devices. For example, traction inverter, DC-DC converter. These are the voltages at different levels. See, this is a 12 volts. And also there is a trend towards getting rid of the 12 volts in the vehicles and going directly for 48 volt system. For example, Tesla Cybertruck, that uses 48 volts for the accessories. The main battery is still 400 volts, but the auxiliary battery is 48 volt system. So these are all the standard. This is a boost converter, full bridge converter, and then you can use it. Or this is if you want 800 volt system, then 400 volts. This is the interleaved 3-phase boost converter. and this is the inverter. So power electronics in electric vehicles, onboard chargers, you can use silicon carbide MOSFET or silicon MOSFET, gallium nitride. I will talk a little more about this wide bandgap devices later. And the DC-DC converter, onboard charger can be about 3 to 30. Mainly it is a level 2 charger is about 22 kilowatts. And DC-DC converter can be 1 to 5 kilowatt depending on the vehicle, because some vehicles are like a mobile home. So everything is there in the vehicle. They can as well live in the car. They have microwave oven, they have a refrigerator, everything, and they can put a bed and sleep there. That there are few people do like that. Then you need a higher power converter, DC-DC converter. Then chargers. There you go. DC charger is a fast charger, external charger. And then the inverter can be 5 to 600 kilowatt. Silicon carbide MOSFET, silicon IGBT, or any of them. Then there is a boost converter, which I mentioned earlier. If the battery voltage is lower and the inverter voltage is higher, you need to have a boost converter. And then the thermal management system. See how much of power electronics is required. It is basically an electric vehicle now with the power electronics on the wheels. Software people call it a software on the wheels. And power electronics people can call it as power electronics on the wheels. So that much of power electronics is required in an electric vehicle. So I just want to give an idea about what type of power converters are used in different applications. For example, the high voltage DC-DC converter, you need, that is the converter, 14 volts converter. We generally use a dual active bridge inverters, or sometimes just a bidirectional. You can use a isolated bidirectional converter, or here it is just an isolated converter. This is not a bidirectional here, but you can also, this is the isolated DC-DC converter. This is isolated. So you have a high voltage, then you convert it to high frequency AC and put a transformer, and then it converts to DC. So 14 volts to this one. So that is one. And this is a bidirectional. This is the other one, DC-DC converter between the battery and the inverter, that is 650 volts. I'm not going to details of operation of all these converters here. So 400 volts, if you want a higher voltage, 650 volts, like in Toyota Prius, you put a boost converter. And also you can also charge the batteries 400 volts by bidirectional. It acts as a buck converter in this direction. One side it is a boost converter, for example. So, for example, Toyota Prius, the first generation was 270 volts, second 500 volts. The next generation is 650 volts. So just to give in a block diagram format, we'll start. So this is the battery, and this is the propulsion motor. Okay, this is the propulsion motor. This is the battery. So batteries can provide about 20 kilowatt, 50 kilowatt you need for the propulsion motor in Toyota Prius. So 20 kilowatt, this is at a certain voltage. This is at 202 volts, and this is 500 volts. Here, this is the second generation system. So this acts as a boost converter. So you turn on this device, then current circulates. When you turn off, that will go like this. So the battery provides 20 kilowatts, and there is a generator. Generator is driven by the engine. It can provide another 30 kilowatts. So totally 20 plus 30, 50 kilowatts comes here. So that is how the Toyota Prius 2 works. And the next generation of Prius, that is a 650 volts, almost similar architecture, but they made the voltage at 650 volts. So you will see more details about the power electronics here. So this is the inverter, and this is the battery, and this is that boost converter, which I just talked. And this is the generator. Basically, this rectifier, this is an active rectifier, basically, because the generator produces AC, it is converted to DC. Okay. So that is how the Toyota Prius of the hybrid electric vehicle work. So total propulsion system in a hybrid or an electric vehicle is, so this is the battery, this is an inverter, it goes to the motor, then it has to be controlled, the motor is controlled. So right now, the trend, all the automotive manufacturers, they use the vector control or the field orientation control. The field orientation control enables an AC motor to be operated like a separately excited DC motor, where the torque and flux can be independently controlled. They are decoupled. Okay, so I have acceleration signal, braking signal, vehicle, and torque, and then it goes to the vector control, then PWM drive system, and then it goes to the inverter. Yeah, I don't know why it switches. Then this is the DC AC inverter. You supply the inverter, the DC voltage, the output will be variable frequency, variable voltage. So generally everybody uses anyway pulse width modulated. So there are different types of pulse width modulation: sinusoidal pulse width modulation, space vector modulation. The current trend is to use the space vector modulation because it can be easily implemented digitally. So there are 8 states because there are 6 devices. So they are fired at a certain sequence, or they are turned on at a certain sequence, then it will be space vector. You might have studied all those things. And then this is the important one, PWM rectifier. As I mentioned, Toyota as a generator, the generator output is AC, AC is converted to DC. The advantage of using the PWM rectifier is you can control the input power factor. Power factor can be even 0.98 to 99. You can have it with a PWM rectifier. So this is the AC and this is the DC. So, or in electric vehicle, for example, when you are slowing down the vehicle or when you brake the vehicle, it slows down, right? At that time, the motor acts as a generator. So generator produces AC, 3-phase AC. That will be converted to DC and fed it to the battery. So battery is recharge. So that is regenerative braking or regeneration. So that the PWM, so the same inverter, when it is acting as a motor, it acts as an inverter, providing the variable frequency, variable voltage to the motor. When it is acting as a generator, it acts as a rectifier. So that is the advantage of using the PWM rectifier. So again, they have to be either MOSFET or IGBT. So you cannot use the diode because the diode is only unidirectional. So you can use the same thing. So PWM rectifier is a very common thing. So I'm not going to explain about the operation principle of all those things, but I just want you to note down these are all very commonly used in the industries. So that is how the PWM operation. This is the generator voltage, and then this is the DC. You can control reference and PWM generator. So that is about the electric vehicles, power electronics. Let us look at the hydrogen-based vehicles. So I just listened to a few minutes in the past lecture. I think the previous speaker talked a lot about the hydrogen and fuel cells. I'm not going to discuss as much as he has done, but I think most of you know how a fuel cell works. If you want to understand how a fuel cell works, this is the only figure diagram you need. That's all. You don't need any other diagram. A fuel cell is like a battery. You supply the hydrogen. Hydrogen is the fuel. Fuel is supplied at the anode and the oxygen at the cathode. And generally in all the fuel cell vehicles, we use the PEM fuel cells. That is the best. PEM fuel cell operates around 18 to 100 degrees Celsius. There are other types of fuel cells like solid oxide fuel cells, molten carbonate, and others. We cannot use it for propulsion, but solid oxide fuel cell can be used for onboard power generation, which operates around 800 to 1000 degrees Celsius. But PEM fuel cell is faster than the PEM fuel cell. Solid oxide fuel cell takes ever to start. It can take, depending on the power, it can take 1 hour to 1 day. So, whereas PEM fuel cell, you can start in a few milliseconds. So, you supply the hydrogen at the anode and oxygen at the cathode, and in every fuel cell, the fuel is always supplied at the anode. And so at 80 degrees Celsius, and there is a catalyst. With the help of the catalyst, the hydrogen dissociates into hydrogen, ion, and electrons. And this is the proton exchange membrane. So the proton exchange membrane allows only the hydrogen ions to flow through it, not the electrons. So the electrons have to flow through the external circuit here. So the external circuit, say here it is one cell I've written, but generally there will be hundreds of cells in series, flows through the external circuit, and the hydrogen ion, or called the proton, flows to the cathode. And here, this electrons coming from here and the hydrogen ion or the proton combines with the oxygen that is supplied, produces water. So what is that we produce? We produce the electricity and we also produce the water. Okay. So by supplying hydrogen at the anode and the oxygen at the cathode, using the PEM fuel cell, we could generate the electricity. And of course, there are a lot of other details you need to worry about, what voltage and all those things. We will not, I think the previous speaker, he must have done a great job in explaining all those things. So I'm not going to details of this, but we'll go into the fuel cell vehicle itself. So a fuel cell vehicle also has a lot of components. It is almost like an electric vehicle. You still need the electric air condition, you need the battery cell, you need all the other components, 14 volts, and you need to have a stack. Stack means number of cells are connected in series. Generally, a fuel cell is operated at around 0.7 volts. So if you want to have with 100 volts at the output, so you need to have about 144 cells in series. Okay, 144 cells in series have to be connected. So then you can get at load about 100 volts. So the fuel cell stack is there. When we were working on in early days, during 90s, when we were working in General Motors on fuel cell vehicles, we were putting the reformer. The reformer is the one produces hydrogen from any fuel, any fossil fuel. Then it was in the trunk. If you open the trunk, it was looking like a chemical plant. Then the automotive company decided, even Chrysler, I worked on the first gasoline reformer based fuel cell vehicle for the Chrysler. Now there is no Chrysler, it was bought by Stellantis, but that was in 1993 or 94. I worked on the DC-DC converter system for that vehicle. Then the automotive company decided, yeah, we don't produce hydrogen, we don't produce gasoline to power the internal combustion engine based vehicle. So why should we produce the hydrogen? Let somebody worry about it. Let us fill up the hydrogen to our vehicle. Let them worry. How do we get the hydrogen is not our problem. So that is why they started using the hydrogen cylinders. Generally, most of the vehicle, right now anyway, Toyota Mirai is the main vehicle that is available on the fuel cell. It uses about 5 kilograms at 700 psi, 5 kg. So 1 kilogram has the same amount of energy as 1 gallon of gasoline. So 1 gallon of gasoline and 1 kilogram of hydrogen have the same energy density. So these are then you need the motor, you need the batteries and all those things. So this shows little more details about you can also combine ultra capacitors in parallel with the fuel cell or the batteries also. So then the power controller, fuel cell stack, humidifiers you need, because the PEM fuel cell has to be kept at a certain humidification level. This is from the Honda fuel cell vehicle. Now they discontinued that vehicle. There is clarity. So if you look at the electrical diagram of a fuel cell vehicle, this is the fuel cell unit, then the output, and then this is the power conditioner. That is for example, fuel cell voltage can be at certain voltage, but here the battery may require certain other voltage. Then you put a DC-DC converter in between, like a power conditioner. So then the rest of the things are similar to the electric vehicle. We have propulsion inverter, propulsion motor, then propulsion system controller, which provides the torque reference. Torque reference is converted to current reference. Then you have to control the hydrogen input. In the case, in the battery, you don't have to worry in the battery electric vehicle, pure battery electric vehicle. And fuel cell is the hydrogen, basically. Hydrogen is the current. So the amount of current is proportional to the amount of hydrogen at the input to the fuel cell. So by controlling the amount of current, you can control the amount of current that is supplied here, basically the power output for a given voltage, by controlling the hydrogen input. So that is why this fuel cell controller is very important. Then also you have to control the air input. What is the amount of air? Because they have to have a certain ratio between the hydrogen input and the air input. And so everything, so that is why the reference for the stack current has to come from the torque reference. That is the same as the current reference, and then you can control the power. So that is how the propulsion system works. For example, or you don't have to have a DC-DC converter. There itself, you can put a battery of any voltage here and put a bidirectional DC-DC converter here and connect it to the inverter directly. And also the fuel cell doesn't have to supply all the power. For example, you need 100 kilowatt. You can also organize such a way that the battery supplies about 40 kilowatt and fuel cell is 60 kilowatt, like that. So you can arrange anything by all these controllers and the fuel cell controller, which control the fuel cell input or the hydrogen input, all these things. So this is the propulsion system for a fuel cell vehicle, basically. For example, Toyota uses this type of architecture. So these are some of the actual vehicle architectures. So this is the same thing as what I have shown earlier. Battery DC-DC converter. There can be another DC-DC converter between the fuel cell and the inverter, and then you can put it here also. So there are different ways of having the architectures connected, how the battery and the fuel cell can be connected together, and also how they are controlled. And also, if you have a battery, because you want the battery serves two purposes. Basically, it can also provide part of the power, and also when you suddenly demand the power, it can come from the battery instead of fuel cell. Generally, we ramp up the power from the fuel cell rather than suddenly, if you need 100 kilowatt, we generally don't use 100 kilowatt directly from the instantaneously. It doesn't come 100 kilowatt from the fuel cell because the hydrogen has to be there. Hydrogen has to be controlled. We don't want to have excess hydrogen already supplied, then it is a waste if you don't use it. Or if you don't provide enough hydrogen, then that may also deteriorate the fuel cell operation over long run. So that is called the utilization factor. We will not go into the details of that. So this is the Toyota Mirai fuel cell. This is PEM fuel cell base. The tank can hold 5.6 kilograms or 10,000 psi, that is 700 bars. So hydrogen, hydrogen is 33.3 kilowatt hour per kg, and gasoline is 13.1. 1 kilogram of 1 kilo, basically 3 kilograms of gasoline is 1 is 1 gallon. So that is why I said 1 gallon and of hydrogen and 1 gallon of 1 kg of hydrogen have the same energy density. So more similar, almost same, I would say. So lithium ion, it uses lithium ion battery of 310 volts, and motor is a permanent magnet motor. And the price, there are 2 versions. One is a higher end version is about $68,000, and the lower end, this is the 2024 prices. So this is how they are all mounted. So this is the power electronic unit, everything here. So Honda has come up with a plug-in fuel cell hybrid vehicle, or they call it FCEV, fuel cell electric vehicle. So means you have a fuel cell and a battery in such a way that Mirai, we don't charge the fuel, this one batteries in the night time, whereas in this one, you can charge the batteries in the night time. That is why the battery capacity is 17.7 kilowatt hour. Means you can operate like a extended range electric vehicle I mentioned earlier. So it is similar to that. You first operate as an electric vehicle using the battery. So the battery state of charge falls below a certain value, or it reaches certain depth of discharge, then the fuel cell can charge those batteries. Or fuel cell can also be, the architecture can be arranged in such a way that fuel cell also can provide the power, both. So it all depends on the architecture. Okay. And also, if you make like an extended range electric vehicle, that is which is a smaller engine is very small, only it charges the batteries as needed. It doesn't supply directly the power to the wheels. So now they are all working on like a cartridges, the cylinders, they call it cartridges. There is the hydrogen cartridges. So you can go to in the highways, you can have it in a Walmart or somewhere, you can have a number of them. So if you want to replace or charge the fuel cell vehicle, you can just go to the Walmart or somewhere and get those cartridges and fix it there. That is some of the things they are working on, but still Toyota has been trying that. So that is the Honda CR plug-in hybrid vehicle. The difference between this and the previous one is it is a bigger battery. Okay. And EV range is 29 miles. And combined is 270 miles total it can provide. Then there are a lot of fuel cell buses are being developed everywhere now. And then there is a lot of work going on in the hydrogen engines also. So means you don't have to, for example, particularly for trucks. So this is the one that is with the hydrogen engine base. So then you don't have to worry about so much of infrastructure for everything. So just use the hydrogen engine. You don't need even power electronics. You replace the current diesel engines by the hydrogen tanks, and then the diesel engine by the hydrogen engine, and the fuel tank by the hydrogen tanks. Okay, so hydrogen tanks are the fuel tanks basically here, and the hydrogen engines. So there are a lot of companies are working on it. They have tried, and for example, this by Mercedes-Benz with the 18-ton truck, 7.5 kilograms of hydrogen per 100 kilometers. These hydrogen engines are being explored even for airplanes. For example, instead of using the jet fuel, we use the hydrogen fuel and replace the jet engine by the hydrogen engine. So there are several companies are looking into that, and Cummins is also developing this type of trucks. But still, it is at the demonstration levels, it is not at the production level. Then you don't have to worry about fuel cell or anything. You don't need fuel cell. You directly have the hydrogen and use it. So the many times people ask me, is it better to use for a car? Is it better to use a fuel cell or the battery electric vehicle? When a battery electric vehicle is there, when do we really need a fuel cell vehicle? My opinion, and in every speech I give, I tell them, for regular cars which we drive, sedans, we don't need a fuel cell. Battery electric vehicle is the best. Because if you look at the difference in the efficiency, considering, for example, you have a 100% energy going into the for developing 100% renewable energy available, and then you want to feed it to the car, then if you use the fuel cell, that 100% renewable energy is to first use to generate hydrogen, electrolysis of water or green hydrogen. Then the hydrogen has to be transported. You have to consider the efficiency of the electrolysis. It can be about 68 to 70, 75% around that. That needs to be considered electrolysis. Then you need to consider, then you have to transport, then the efficiency of the transportation. Then it has to be considered the PEM fuel cell or a fuel cell. Fuel cell efficiency, even though people PEM fuel cell, say about 45%. If you consider all the efficiencies like compressor itself is very bad. It takes a lot of power. All those things you may get about 30%. The overall system efficiency, including the all the accessories and everything. So finally, for a fuel cell, if you consider it will end up in 18 to 20%. On the other hand, so these are the comparison between the fuel cell and the hydrogen vehicles. So they are more or less similar. But on the other hand, for a pure electric vehicle, same 100% renewable energy, you need to transport, and then it goes to the charger. And then maybe you may have to, if it is an AC, you have to step it down and then convert to right voltage, and then use it as a charger. Chargers are generally about 90%, 88 to 90%, and then you connect to the battery. So basically, you get 75% of the whatever we start with the 100% renewable energy from the beginning for both of them. So you get finally for the propulsion 18 to 20%, for the propulsion battery electric vehicle 75%. Oh, then you may ask, then we don't need the fuel cell at all, vehicles for the transportation. I think we need it still. I would prefer using fuel cell for the buses, heavy duty trucks and others where they don't have it. They have a very heavy batteries, and these batteries have to be charged. Heavy batteries, even with fast chargers, they take a lot of time. When the highway trucks, they don't have enough time to stop and charge the vehicles. So in that case, fuel cells are the best. Then they can use the fuel cell systems that will take. So then in that case, they are the best. Okay. So for heavy duty bus and for ships, fuel cells are the best because there is enough space and all those things. Fuel cells, they go away. And for the airplanes, you can never have a pure battery aircraft like 737 or Airbus 320 or 777 like that. You can have a 3 or 4 passenger, a pure electric aircraft, but not passenger vehicle. A 737 airplane needs another 10 737 airplanes to carry batteries to take care of one battery powered 737 aircraft. So pure battery powered electric aircraft, even with lithium ion batteries, for a commercial aircraft is not possible because of the distance. If it is only short distance, then it's okay. And also they are very heavy. For example, 777, the capacity of the fuel tank is how much? 45 to 50,000 gallons of jet fuel. So this is what I was comparing the battery electric vehicle fuel cell electric vehicle and a hydrogen engine based electric vehicle. So 75% for the battery electric vehicle, the efficiency consider. This is for the fuel cell this is for the truck. And if you look at the internal combustion engine based vehicle, for example, you have again 100% start with distribution, then distribution will take, then the electrolysis, then the transportation it has to go through, then the combustion. Hydrogen engines are not that efficient anyway, great. So all those into effect, finally you get about 15%. But still for the trucks, it may be okay if you are getting all the hydrogen from the renewable energy sources. Okay. So there are a lot of commercial power electronics units available. These are all some of the power electronics. This is the power electronics GM Ultium units. That is why they combine the DC-DC converter and the inverter, everything together. These are the actual practical units. And the trend is to combine the motor and the inverter also together into one unit so that overall power density will increase. So if this is a Borg-Wagner unit, for example, traction motor is 220 kilowatt and total is about 20 kilowatt per kg peak power. Tesla uses a different type of motor because I mentioned, almost all the EV manufacturers, they use the permanent magnet motors, but Tesla is switching over to synchronous reluctance motors with PM assisted. There is a little bit, it is still there is a permanent magnet on the rotor, but very little permanent magnet. It is a synchronous reluctance machine. So you may want to watch. You can also put on the YouTube and put Tesla Model 3 synchronous motor. It will give you this video. So you should watch this, how that one works. So it is basically synchronous reluctance motor. Basic synchronous reluctance motor doesn't use any permanent magnets at all. But the power factor is poor and the efficiency is not that great. That's why you put a permanent magnet, then it becomes more efficient and the power factor will also improve. So this gives an idea of the propulsion system for the various some of the vehicles. For example, Tesla Model Y is a 339 kilowatts and the Cadillac optics, and these are all the different power, and all of them, some of them use the front motor, the permanent magnet motors, rear motor, the induction motor, and Tesla is the only one that uses the IPM synchronous reluctance motor. That is the interior permanent magnet based synchronous reluctance motor. So it is basically synchronous reluctance, but put the magnets on the rotor a little bit, not so much. And the battery nominal voltage, you see each one uses a different voltage. Hyundai is using 800 volt system, and BYD is a different voltage. So there is no particular standard still. And battery capacities are different. And these are all some of the power densities. And these are the inverters. Tesla Model Y is 220 kilowatt, Cadillac Optic is 250. These are all the recent figures. 150 kilowatt. The only thing in all this electric vehicle, when I give a presentation this year, if I have to use the same presentation next year, I have to change several things because the technologies are advancing every day. Every year you will see so much of change. So I need to keep on updating my presentations, these things. So 600 kilowatt, all those. So this is the DC link system voltage, and this is semiconductor they use. Silicon. Now more or less everybody is switching over to silicon carbide devices. And so in few years, everybody uses silicon carbide devices for the propulsion inverter and for the gallium nitride device for the DC-DC converters. Okay. And also this is from another company, H3X. So they try to integrate the motor and the inverter together, and they get 12 kilowatt per kg. They are also looking this type of motor drive system for the aerospace system also. So this is a 250 kilowatt system. Okay. So as I mentioned earlier, the trend is to combine the propulsion. Jumps, I don't know why. So the trend is to combine the propulsion inverter, DC-DC converter, and the onboard charger. Okay. So Tesla, for example, Tesla makes their own system, power electronics, everything. And so they have the overall dimensions like this. And this is the SAIC. They use from UAES. Again, it is the Chinese company. And this is the Innovance, is again another Chinese company, Xpeng. They are also doing a lot of work in the area of electric vehicles. They are also working on the flying cars. They are working on both eVTOL and flying cars. The difference, they are not the same. eVTOL is like air taxi. It can only fly in the sky. So you have to go, for example, airports. They use it so that air taxi, they use it like an air taxi. Flying car, you can go on the road as well as on the sky. There are a few companies working on that. Hopefully one day everything will be flying cars. So then we'll talk about a little bit about the wide band gap devices, which I mentioned earlier. Wide band gap devices, semiconductors are the silicon carbide. Right now it is all mostly silicon carbide and gallium nitride devices, because they have a higher thermal conductivity, they can operate at higher temperatures, they have a higher breakdown voltages, they have a higher mobility, high electrical conductivity, high thermal conductivity, everything when compared to the silicon devices. And also they have a low on-state resistance, silicon, when compared to silicon MOSFETs. So this gives an idea about the band gap. Silicon is 1.1, whereas silicon carbide is 3.0 electron volts. Gallium nitride is 3.4, and diamond is still not being used, but ultimately people are thinking about it, but it will be quite expensive. And mobility. So if you use IGBTs, you can switch up to 10 to 20, 50 kilowatts. You can go with IGBTs. With silicon MOSFETs, you can go up to 100 kilowatts. If you use silicon carbide, up to 1 megawatts. Theoretically, and gallium nitride, if you use up to about 5 megahertz, you can switch. So the trend is to go for higher switching frequencies. So, but the power, gallium nitride is mostly available at 600 volts, but their work is going on 1200 volt gallium nitride devices. But silicon carbide is available at higher voltages like 1700 volts or even higher. And they can also go for high power inverters. So for traction inverters, 15 kilowatt to 400 kilowatt, EV charger 3.3, 22 kilowatt, and booster up to 5 kilowatt to 5 megawatts. You can use all these silicon carbide devices. Okay. So the Toyota Camry, for example, they switched from this is with silicon devices, their inverter power unit, and this is with silicon carbide devices. So with they could reduce this using silicon carbide devices so much in size. And this is the Tesla Model 3 inverter. So after using silicon carbide devices, these are 220 kilowatts. It is so small. Okay. This is the gallium nitride based charger. So Shangan Automobile, that is near Chongqing in China, they also make a lot of electric vehicles. There are so many electric vehicle manufacturers in China, maybe at least about 50, maybe. So they demonstrate first one gallium nitride based onboard chargers. So they claim 96% efficiency with that is the DC-DC converter for accessory units. That is from also that is this DC-DC converter for bringing down to 14 volts from the high voltage battery. they also demonstrated gallium nitride charger. So this is with the silicon and this is with the gallium nitride. So the Department of Energy in the United States is spending a lot of money on advancing this semiconductor devices for the gallium nitride and wide band gap, in general wide band gap devices. You can see that if you use the silicon carbide devices when compared to silicon IGBT, silicon carbide MOSFET, how much the power loss in the inverter reduces from 9.1% to 2.12%. In a EPA city cycle, it is in the highway cycle, highway driving cycle. So silicon is 2.29% and silicon carbide MOSFET is 0.34%. So that is why the trend is to go for silicon carbide and gallium nitride devices in the automotive systems. And many companies are already replacing the silicon devices with silicon carbide devices, but still they are quite expensive. So again, the United States Department of Energy has created the electrical and electronics technical roadmap where we have to be in 2030, 2035 in terms of the power level. These are all for the electric vehicles. Okay. The power electronics has to be, the cost has to be $1.2 per kilowatt. That is the target, power electronics target. And that is for about 225 kilowatt system traction inverter. And for the motor, for a 225 kilowatt motor operating at 800 volts, the cost has to be $1.47 per kilowatt. That is, if you convert it into rupees, that is how much? About 1,200,000 or 1,300,000? No. I mean, it's not 100,000. 140 rupees, right? No. 140, 1.47 is about 130 rupees is $1.47, right? Yeah. No, $1 is about 87, so 1.47 is about 130 rupees. I think so. You can correct me later. So I am not sure that is how achievable in India. I'm not sure, or maybe I'm not sure. Somebody can tell me after this. And then the EDS, that is the combined traction, overall traction drive system. They are aiming at $2.67 per kilowatt. That is the inverter and the power electronics and the drive motor. And this is the DC-DC converter targets. And this is for the technical targets for the onboard charger. So right now there is a lot of work going on still in the area of new topologies of the inverters and power converters, because we are trying to go for a high power inverters and all those things. Even multi-level inverters are being investigated, particularly for the trucks. The others, of course, high temperature wide band gap devices, packaging, capacitors are very important, because we don't get a high temperature capacitors, maybe 104, but or maybe even less. Even 104 getting is sometimes difficult. Then if you are looking for 200 to 300, 250 degrees Celsius capacitors, we hardly get it. So vehicle charging. So there are a lot of technical targets for the Department of Energy. So the most important thing is not to use the permanent magnets, non-heavy rare earth machines. That is what the major for the motors. And durable increase. So all these things, what we discuss, are still being considered, like high power density systems and increase in the reliability, durability, high frequency wide band gap devices, fast charging, DC charging infrastructure, thermal management. All those things have to be still further improved. But a lot of work has already been done. We are much better more than we were 10 years ago. But still further overall to reduce the cost and improve the performance and the range, we still need to work on it. So what are the technical trends for the future? Is the battery voltage is going to go up 800 volts. And of course, there are a lot of issues that have to be considered. And new motors like synchronous reluctance, even though all of them use the permanent magnet motors, there is the interior permanent magnet motors, except Tesla and the Model 3 they use, or Model 3 and Model Y, interior permanent magnet based synchronous reluctance motors. But various motors architectures, high switching frequency, bidirectional onboard chargers, these are all the trends, and high level of integration, motor, inverter, and the DC-DC converter, all those things. So where have we come and what are the futures? So in the area of energy storage, we started with lead acid. That was our first electric vehicle was based on lead acid battery. It was weighing 900 pounds. So then we switched over to nickel metal hydride, then lithium ion, then solid state battery is the next one. By next year, I think several vehicles will have a solid state battery. Then maybe lithium sulfur, sodium ion could also be another possibility for the next one, comparing the cost of solid state battery. Sodium ion would be better. Solid state battery still uses lithium. You still need lithium. Lithium air is very good because lithium air will have 11,140 watt-hour per kilogram. There is a theoretical. Almost equivalent to gasoline. Gasoline is 12,700 watt-hour per kg and lithium air. So we don't get a lithium 1,140 watt-hour per kg in practice. Even if we get 1,000 or even 800 watt-hour per kg, that will be great. So, but there are a lot of challenges. Motors, we were originally DC motors, then induction motors, PM motors. Now we are looking at synchronous IPM motors. With all these permanent magnet motors and all those things, I think induction motors, I think we need to go back to induction motors and look at it. That is what I think. Induction motors have a lot of potential. Even though there are a lot of advancements in induction motors, they are not that bad in efficiency, maybe slightly less, but induction motors could be looked at it if PM has that much challenges. Power electronics, now everything will be based on silicon carbide and gallium nitride, but the trend will be to integrate the motor, inverter, DC-DC converter. Charging, conductive charging, DC fast charging has become more and more common. Wireless charging will be predominant, particularly for fleet vehicles, and also with V2G and G2V systems with 800 volts. And then, so all those things, then the trend is to go for autonomous vehicles, then the connected electric vehicles, intelligent connected and autonomous vehicles. Then if you have all these things, you can have a remote driving. Means if people cannot drive, you can ask them to still sit in the car, then you can program the car where to go and it will go and drop them and come. Then vehicle to grid, smart energy system, then ultimately we will have flying cars. Now we already, in few years, eVTOL will become more common. A lot of cities like Dubai Airport, Los Angeles, Saudi Arabia, they are all investigating eVTOL systems. And then flying cars will be the one which goes on the air, which goes in the sky. So this is my last slide. So power electronics is the enabling technology for transportation, electrification. Power electronics is the software, the power electronics on the wheels in electric vehicles, whether it is an electric vehicle or a ship or a drone or airplane, we need power electronics. Of course, we also need other systems, and power electronics is the enabling technology. So with this, I will stop and you can ask me questions. I need to get back into this. Yeah. I think I need to stop sharing. Okay. Any questions?
Thank you very much, sir. Dear participants, now the session is open for question and answers. Sir, shall we start with the chat box? Already we have one question from Dr. Rajahmundry.
Okay.
Sir, can you shed some light on potential research areas in V2G systems? That's the question asked by Dr. Rojo.
Yeah, the potential areas are still it is being combined. For example, your car may be able to provide the power that is required, but many utilities are not, in the United States, many utilities are not allowing to power the car, means supply the grid from the car, means the car should not be powering the grid because it may affect, for example, it may affect the harmonics, it may affect the EMI in the system, and also when it has to be, when there are already a lot of power in the utilities, and then you want to supply additional power, then it is a problem. And then how do you pay for all the customers who supply the power? So what is the effect on the grid? Okay, when all these cars started supplying the power to the grid, that is one of the major things that needs to be incorporated. And also there is a major issue, a lot of researchers are looking at it. What happens if we are talking about millions of vehicles are supplying the electricity to the grid? What is the effect on the grid? Okay, if it is the grid is from renewable energy sources, what is the effect? If it is a traditional grid, how it is going to be affected? If it is a microgrid or if it is a hybrid grid, so how all these things are affected is a major issue that needs to be still addressed. So it is still not very common, even though there are a lot of electric vehicles, but they are not using for powering the grid. But there are some places, for example, London, there is a bus station, they are all electric vehicles, electric buses, they are supplying the power to the grid. So they have to make special arrangements for that. So that is the major research that needs to be investigated. What is the effect on the grid if so many vehicles are powering the grid, and also what is the best scheduling? Because what is the best way to schedule all those things? Then how do you also protect the overall system? Okay, these are some of the things that are being investigated. Okay, anybody else has any questions?
Sir, good evening, sir. Sir,
Yeah.
myself, Dr. Suresh from Godavari Institute of Engineering and Technology. Sir, actually, in the power electronics, we have to use for conversioning, sir, like for DC to DC or DC to AC, sir. So, what are the present converters which are used in hybrid electric vehicles, sir? What are the latest power electronic converters?
For the inverter, I think more or less everybody use the 2-level inverters with the space vector PWM.
Okay, sir.
Even though we have done a lot of work on the resonant converters and all those things, ultimately cost and all those things and the number of components, the reliability, and everything is being considered, then this one 2-level inverter is the common. That is the one with 6 devices. So only thing, they are all based on the silicon carbide device, which I shown you the diagram already. They are all based on switching over to silicon carbide, from silicon IGBT to silicon carbide MOSFET devices. That is the trend that is being done. So the replacement or the design of the system based on silicon carbide is the trend. And for the this one, DC-DC converters, it is the they are right now, to reduce the costs, they don't have to be bidirectional, the 14 volts, but they use a simple isolated converter. I think I showed you the diagram. With the transformer, you convert you bring the high voltage battery into a high frequency AC, and then put a transformer, high frequency transformer, and then rectify it, and you get a 14 volts. So that is the technology that is mostly used. Means different versions of the same thing. And for the chargers, again, different companies, they use different types of chargers. There right now, most of them are unidirectional. So convert the high voltage to the required battery, the step down, and then most of them are providing the isolation. For the fast chargers, isolation is very important. They provide the isolation. Otherwise, in the onboard chargers, again, there are different technologies being used. Like basically, you have to bring down or it depends on what is the input voltage in the case of chargers. For example, generally in the United States, we charge houses have only single phase. Yes, we don't have a three phase in our house. In Europe, many houses have three phase system also. So if they have a three phase or a single phase, they can use the active rectifiers. Then active rectifier is converted to DC, and then you have a DC-DC converter and charge the batteries. So that is the one. Sorry, somebody asked something?
Sir, I am submitting a research proposal on hybrid electric vehicles, sir. Regarding that, what are the problems we have considered for writing a proposal from your suggestion, sir?
Hybrid vehicle has a very vast range of architectures. I don't know what architecture, it depends. For every architecture, it's its own problem. I have a diagram with, there are 22 different architectures you can have for a hybrid vehicle. So I'm not sure, because everything what I suggest for one architecture may not be valid for the other architecture. So that is a separate discussion. Because and also if it is a plug-in hybrid vehicle, then you need to worry about something else. So, and if it is an extended range electric vehicle, it's a different. And if it is a parallel hybrid vehicle, it's a different. And for example, Toyota Prius is a series hybrid vehicle with a planetary gear system.
Yes, sir.
So if you are just looking at the power electronics, the power electronics has become very standard now. So, yeah.
Okay, sir. Thank you, sir.
Else? Okay. If you don't have any questions, thank you. We can stop here.
Yes, thank you, sir. Thank you very much. So if there are any further questions, so you please feel free to share with us so that we can communicate to Dr. Kaushik Rajashekara, sir, so that we can get the response later.
Okay, thank you.
Thank you very much. Thank you for your time, sir, for sharing a very insightful session to our participants. So you have take us through the intricacies of all the power electronics without.
Yeah. All right. Bye.
Yeah. Thank you, sir. Thank you once again.
Thank you very much to all the participants and the students.
Thank you, sir.
Thank you, sir.
Thank you all. So we will end the session for day 2. So tomorrow we will proceed with the session 5 and 6. Thank you very much.